Imagine the night sky above you. The stars you see are not eternal flames, but temporary beacons in cosmic darkness. As you gaze upward, consider that everything you observe, every glimmering point of light, every galaxy, every atom exists within a universe that is still, by cosmic standards, in its youth. In this moment of universal adolescence, the laws of physics appear immutable. Gravity draws matter together. Light travels at a constant speed. Energy cannot be created or destroyed. These are the bedrock truths upon which our understanding rests. Yet what if these foundational principles are not eternal? What if the physics we know is merely a phase, a temporary consensus of cosmic forces that will, over unimaginable stretches of time, begin to shift, to unravel, to transform? This is not a story of catastrophe, but of metamorphosis. As the universe ages, as it expands and cools over trillions upon trillions of years, the behavior of reality itself may change in ways we can barely comprehend. The universe was born in fire approximately 13.8 billion years ago. Our sun, merely middle-aged at 4.6 billion years, will burn for perhaps another 5 billion. But what of the time beyond? What happens in 1 trillion years? In 100 trillion? In numbers so vast we have no intuitive grasp of their meaning. We invite you to journey with us to the end of time itself, to witness the strange behavior of physics at the end of the universe. Not as an observer, for no observers will remain, but as a dreamer might visit places that exist only in possibility. In this cosmic twilight, the familiar laws that govern our reality begin to show their age. They reveal unexpected behaviors, paradoxes, and transformations. The universe we know fades, and something else, something stranger, emerges in its place. Let us begin our journey not at the beginning, but here, in the present, with the physics we know. For to understand how things end, we must first understand how they are. The silence of a fading sky speaks volumes. Imagine standing on a distant world, many billions of years from now. The stars have grown fewer, the night is darker. The universe has grown quieter as the galaxies drift farther apart. This is the first hint of what awaits us at the end of time. A gradual slowing, a cosmic exhale that stretches across eons. Time itself is a river with currents that change. Near the beginning of the universe, during those first explosive moments after the Big Bang, time flowed differently. Matter and energy existed in states we can barely understand. The 4 fundamental forces we know today were once unified in ways our equations still struggle to describe completely. And at the end, time may flow differently again. It might stretch, dilate, or even lose meaning altogether. When nothing changes, when no events occur, can time be said to pass at all? This is one of the profound puzzles that awaits us at the universe's final frontier. The laws of physics as we know them emerged from the cooling aftermath of creation. They crystallized as the universe expanded, as matter formed, as complexity arose. These laws appear perfect, mathematical, eternal. The orbit of an electron around a nucleus follows the same equations, whether it happens in our bodies or in a galaxy billions of light years away. The speed of light remains constant regardless of the observer. Mass and energy convert according to Einstein's famous equation. But these laws exist in a universe that still has structure, that still has temperature differences, that still has time flowing in a clear direction. What happens when these conditions fade? The universe today exists in a delicate balance. Stars burn by converting mass into energy, illuminating their surroundings, enabling life. Galaxies spin, held together by dark matter we cannot see, but whose gravitational effects we can measure. Black holes devour matter, while paradoxically emitting faint radiation. Planets orbit, comets soar. Everything moves in a complex dance governed by rules we have painstakingly discovered. Our scientific journey has revealed the clockwork of reality, from atoms to galaxies. We understand the forces that bind nuclei, that form molecules, that shape planets and stars. But this knowledge has come to us during a specific cosmic epoch, a time when the universe is neither too hot nor too cold, neither too dense nor too sparse. As we venture forward, you will see how this balance shifts, how, over vast stretches of time, the universe changes state, how different processes dominate during different eras. how everything we know transforms as cosmic age accumulates. The journey will take us through the lifetimes of stars, through the death throes of galaxies, through the slow decay of matter itself. We will witness the rise of a universe dominated by black holes, and then their eventual evaporation. We will explore cosmic epochs so far from our own that the physics governing them might seem alien to us. And through it all, we will contemplate the most profound questions. Is time infinite? Does information survive eternally? Could consciousness find a way to persist? Is there a purpose to existence when all familiar structures have dissolved? This is the strange behavior of physics at the end of the universe. Not just an ending, but a transformation. Not just a conclusion, but perhaps a transition to something else entirely. Join us now as we begin our journey through deep time. We must first understand their present state. Our universe operates according to principles so reliable that we call them laws. These are not legal statutes created by cosmic legislators, but patterns so deeply woven into reality that they appear inviolable. Let us explore these fundamental forces and constants that govern everything from the dance of atoms to the movement of galaxies. The universe we inhabit today is a place of exquisite balance. On a clear night, far from city lights, one can observe thousands of stars scattered across the vault of heaven. Each is a nuclear furnace converting matter to energy, according to Einstein's famous equation. Energy equals mass multiplied by the speed of light squared. This elegant formula, perhaps the most famous in all of physics, demonstrates the profound connection between matter and energy, showing them to be different expressions of the same underlying reality. Gravity, the most familiar force to us, binds us to Earth and keeps planets orbiting their stars. What we experience as weight is actually the gentle hand of our planet pulling us toward its center. Though it feels powerful in our daily lives, gravity is actually the weakest of the four fundamental forces. Its strength follows an elegant inverse square law, becoming weaker exactly in proportion to the square of the distance between objects. Despite this relative weakness, gravity dominates the largest scales of the cosmos because it acts over vast distances and, unlike the other forces, is always attractive, never repulsive. The classical theory of gravity, formulated by Isaac Newton in the 17th century, describes the force as acting instantaneously across space. Any two masses attract each other with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. This simple relationship successfully explains the orbits of planets, the tides of oceans, and the fall of apples from trees. However, Newton's theory contains a profound puzzle. Unlike other forces, gravity seems to act at a distance, with no apparent mechanism for transmitting its influence from one object to another. This mystery persisted for over 2 centuries, until Einstein offered a revolutionary new perspective that completely transformed our understanding of gravity's nature. Einstein revealed that gravity is not merely a force but a curvature of spacetime itself. Mass tells spacetime how to bend, and bent spacetime tells mass how to move. This insight, formalized in the general theory of relativity, transformed our understanding of the cosmos. Black holes, gravitational waves, and the expansion of the universe itself all emerge from this profound realization about the nature of gravity. The electromagnetic force governs light, electricity, magnetism, and the chemical bonds that hold matter together. It binds electrons to nuclei, creating atoms. It links atoms together, forming molecules. Every color you see, every texture you feel, every chemical reaction that sustains your body depends on this force. Electromagnetic waves, including visible light, radio waves, X-rays, and gamma rays, are all manifestations of this same fundamental interaction. The classical theory of electromagnetism, formalized by James Clerk Maxwell in the 19th century, unified electricity and magnetism, showing them to be aspects of a single force. His equations revealed that oscillating electric and magnetic fields could travel through space as waves, moving at precisely the speed of light. This breakthrough suggested that light itself was an electromagnetic phenomenon, a prediction later confirmed by experiment. Quantum theory transformed our understanding of electromagnetism even further. Light, previously understood only as a wave, revealed particle-like properties as well. These light particles, called photons, carry discrete packets of energy. Similarly, Electrons, thought to be particles, exhibited wave-like behaviors. This wave-particle duality, a cornerstone of quantum mechanics, demonstrates that at the most fundamental levels, our everyday concepts of waves and particles break down, replaced by quantum entities that defy simple classification. Unlike gravity, the electromagnetic force can both attract and repel. Opposite charges pull toward each other, while like charges push away. This dual nature creates a rich complexity in how matter behaves. The electromagnetic force is carried by photons, particles of light that travel at the cosmic speed limit, 299,792,458 meters per second, in vacuum. This constant, simply called the speed of light, represents a fundamental boundary in our universe, a speed that nothing with mass can reach. Delving deeper into the structure of matter, we encounter the strong nuclear force. Over 100 times stronger than electromagnetism, this force binds protons and neutrons together in atomic nuclei. Without it, the electromagnetic repulsion between positively charged protons would tear nuclei apart instantly. The strong force operates only at incredibly tiny distances, approximately the width of a proton, about 10 to the negative 15 meters. Beyond this range, its influence fades rapidly. The strong force exemplifies how different physics dominates at different scales. At distances smaller than the proton itself, the force is carried by gluons exchanged between quarks, the even more fundamental particles that compose protons and neutrons. These gluons not only transmit the force, but also carry the color charge that generates it, making them quite different from photons, which carry electromagnetic force, but have no electric charge themselves. This self-interaction of gluons creates a force that behaves unlike any other we know. The strong force is carried by particles called gluons, which bind quarks together to form protons and neutrons. The theory describing these interactions, quantum chromodynamics, reveals a surprising property. Unlike other forces that weaken with distance, the strong force actually strengthens as particles try to separate, like an elastic band that pulls harder the more it stretches. This phenomenon, called confinement, explains why we never observe isolated quarks in nature. The fourth fundamental force, the weak nuclear force, governs certain types of radioactive decay and plays a crucial role in the nuclear fusion processes that power our sun and other stars. Without the weak force, stars could not shine, and the elements necessary for life could never have formed. This force acts over even shorter distances than the strong force and is carried by particles known as W and Z bosons, which have substantial mass. Unlike the massless photons of electromagnetism, the weak force has a remarkable property. It is the only force that can change the flavor of quarks, transforming one type into another. This ability enables the nuclear reactions that convert hydrogen into helium in stellar cores, releasing the energy that ultimately sustains life on Earth. The weak force also treats left-handed and right-handed particles differently, breaking a symmetry that the other forces respect. These four forces, gravity, electromagnetism, strong, and weak, constitute the fundamental interactions that govern our universe. Modern physics seeks to unify them, to show that they are different aspects of a single, more fundamental interaction. At extremely high energies, such as those present in the earliest moments after the Big Bang, the electromagnetic and weak forces merge into a single electro-weak force. Theories that attempt to unify this electro-weak force with the strong force are called grand unified theories, while the ultimate goal of including gravity in this unification remains the holy grail of theoretical physics. Beyond forces, our universe is characterized by certain fundamental constants. These are values that, as far as we can tell, remain the same throughout space and time, providing a consistent framework for physical laws. The speed of light, which we've already mentioned, is one such constant. Another is Planck's constant, which governs the behavior of the quantum realm and sets the scale at which quantum effects become significant. The gravitational constant determines the strength of gravity throughout the universe. The fine structure, constant, characterizes the strength of the electromagnetic interaction. The masses of elementary particles, from electrons to quarks, appear to be fixed values that help determine the structure of matter. The Boltzmann constant relates energy to temperature, while the cosmological constant influences the expansion rate of the universe itself. These constants seem perfectly tuned to allow for the emergence of complexity and life. Slight changes to their values would result in a radically different universe, one likely incapable of supporting stars, planets, or biological organisms. This apparent fine-tuning remains one of the great mysteries of physics. Is it mere coincidence, the result of some deeper principle we have yet to discover, or evidence of something more profound about the nature of existence? Consider the fine structure constant, which determines the strength of electromagnetic interactions. Its value, approximately 1 divided by 137, appears arbitrary from a theoretical perspective. Yet if it were just a few percent larger or smaller, atoms could not form stable structures, chemistry as we know it would be impossible, and life could not exist. Similarly, the precise balance between the strength of the weak nuclear force and the electromagnetic force enables stars to burn steadily for billions of years, providing the stable energy sources necessary for life to evolve. The cosmological constant, which characterizes the energy density of empty space and drives the accelerating expansion of the universe, presents perhaps the most extreme example of apparent fine-tuning. Theoretical calculations suggest its natural value should be enormous, yet observations show it to be incredibly tiny, approximately 10 to the negative 120 in natural units. If it were much larger, the universe would have expanded so rapidly that galaxies, stars, and planets could never have formed. These examples of fine-tuning have led some physicists to propose the anthropic principle, which suggests that we observe these particular values precisely because they allow for observers like us to exist. In a hypothetical multiverse containing regions with different fundamental constants, only those regions compatible with the evolution of intelligent life would contain beings capable of measuring those constants and contemplating their significance. Others search for deeper symmetries or unifying principles that might explain why these constants take exactly the values they do. String theory, loop quantum gravity, and other approaches to quantum gravity attempt to derive these seemingly arbitrary numbers from more fundamental considerations. Perhaps in the ultimate theory of physics, what now appear as independent constants will emerge as necessary consequences of a single unified framework. The laws and constants we observe reflect a universe governed by symmetry, order, and conservation principles. Symmetries in physics represent profound insights into the structure of reality. The conservation of energy, for instance, arises from the symmetry of time, the fact that the laws of physics work the same way, regardless of when they operate. The conservation of momentum stems from the symmetry of space, and the conservation of charge reflects another fundamental symmetry in how particles interact. Our universe maintains these perfect balances. In every interaction, energy, momentum, charge, and certain other quantities are precisely conserved. Nothing is truly lost, merely transformed. A star's energy becomes light, which may become the chemical energy in a plant, which may become the kinetic energy of an animal. Each joule, each unit of energy, remains eternally in the cosmic ledger, though it changes form continuously. This principle of conservation extends beyond energy. Angular momentum, the quantity that describes rotational motion, remains constant in closed systems. This is why ice skaters spin faster when they pull in their arms, why the Earth maintains its 24-hour rotation, and why galaxies continue their stately spiral motion over billions of years. The total electric charge in the universe appears constant, neither created nor destroyed, merely redistributed. Quantum mechanics, our framework for understanding reality at the smallest scales, introduces probability and uncertainty into physics. Yet even in this seemingly chaotic realm, conservation laws hold firm. When particles interact, quantum numbers like charge, lepton number, and baryon number remain precisely balanced. The quantum world, for all its counterintuitive behavior, still operates according to deep mathematical principles. The elegance of these conservation laws points to a universe with underlying mathematical harmony. Physicist Eugene Wigner once wrote about the unreasonable effectiveness of mathematics in describing the natural world. Indeed, the deepest laws of physics often exhibit a mathematical beauty that suggests we are uncovering something fundamental about reality. not merely constructing useful models. This mathematical underpinning of physical law appears in numerous guises. The inverse square relationship governs both gravitational and electromagnetic forces. Wave functions describe the probability distributions of quantum particles. Differential equations capture the evolution of fields and systems over time. Symmetry groups classify particles and their interactions. Again and again, mathematical structures developed by pure reason turn out to match the empirical structure of reality with astonishing precision. Consider the Dirac equation, which predicted the existence of antimatter before any experimental evidence was found, or the way general relativity predicted gravitational waves and black holes decades before technology allowed us to detect them. In each case, mathematical exploration revealed aspects of reality not yet observed, but later confirmed. This predictive power suggests that mathematics is not merely a human language we impose on nature, but something more deeply connected to the fabric of existence. The second law of thermodynamics stands somewhat apart from these perfect conservation principles. It states that entropy, a measure of disorder or randomness, tends to increase in closed systems over time. While energy is conserved, its quality or usefulness degrades. This introduces a fundamental asymmetry to time, an arrow pointing from past to future that manifests in our everyday experience. We remember the past but not the future. Eggs break but don't spontaneously reassemble. Heat flows from hot objects to cold ones, never the reverse. This entropic principle appears to contradict the perfect symmetries found elsewhere in physics. Most fundamental equations work equally well forward or backward in time, yet our universe shows a clear temporal direction. This tension between time-reversible fundamental laws and the irreversible flow of time as we experience it remains one of the profound puzzles in physics, one that will become increasingly important as we approach the universe's distant future. The physics we observe today operates in a cosmos that, while vast, remains relatively young and energetic. Stars continue to form from cosmic gas clouds, galaxies merge and evolve. Black holes grow by consuming matter and energy. New heavy elements are forged in supernovae and neutron star collisions. The universe remains dynamically active, with energy gradients that power change and evolution. Our current epoch favors complexity. Atoms can combine to form molecules. Molecules can assemble into cells. Cells can organize into organisms. This nested hierarchy of structures depends on the stability of matter under present conditions, the availability of energy, and the particular balance of forces that characterizes our universe today. For us, living in this balanced cosmic moment, these principles seem permanent. The proton, a fundamental building block of matter, appears completely stable. Current experiments suggest its lifetime exceeds 10 to the 34 years, far longer than the current age of the universe. Atoms form, molecules bond, and complex chemistry unfolds according to rules that seem unchangeable. Stars burn for billions or trillions of years, depending on their mass, following life cycles we can map with high precision. Yet this stability exists in a universe that's changing. The cosmos expanded rapidly during inflation in its earliest moments. It continues to expand today, with that expansion accelerating due to the mysterious influence of dark energy. Galaxies move apart. Energy disperses. The average temperature of the universe, once hot enough to prevent atoms from forming, has cooled to just 2.7 Kelvin, less than 3 degrees above absolute zero, and it continues to cool. The laws we observe today, the constants we measure, the perfect conservation principles and elegant symmetries, all exist within this context. They govern a universe still actively processing the energy released in the Big Bang, still far from any conceivable equilibrium state. They describe reality in what cosmologists sometimes call the stelliferous era, the age of stars, when luminous matter remains abundant and organized structures dominate the cosmic landscape. Our present cosmic epoch is characterized by hierarchies of structure. Individual atoms aggregate into molecules. Molecules form gases, liquids, and solids. These materials concentrate through gravity to create asteroids, moons, and planets. Planets orbit stars, which themselves collect into stellar clusters and galaxies. Galaxies form groups, clusters, and superclusters, creating a vast cosmic web of matter that spans billions of light years. This nested architecture of reality emerges from the interplay of fundamental forces. Gravity draws matter together on the largest scales. Electromagnetic forces create chemical bonds and determine material properties at intermediate scales. Nuclear forces maintain stability at the smallest scales. Together, they create the conditions for complexity, allowing the emergence of phenomena like weather systems, geological processes, biological life, and conscious thought. But what happens when this era ends? What occurs when stars exhaust their fuel, when galaxies complete their mergers, when black holes have consumed available matter, when the expansion of space has pulled everything so far apart that no new structures can form? What becomes of our perfect laws then? This is not merely an academic question. The fate of physics itself is tied to the fate of the universe. As conditions change over the vast sweep of cosmic time, the behaviors we observe, the interactions we measure, the phenomena we experience may all transform in profound ways. Some physicists have even suggested that the fundamental constants themselves might not be truly constant over sufficiently long timescales. Consider, for example, how the relative importance of different forces changes depending on the scale and energy we examine. At everyday human scales, electromagnetism and gravity dominate. At nuclear scales, the strong force rules. In the high-energy environment of particle accelerators, the weak force plays a crucial role. In the extreme densities of neutron stars or black holes, gravity overwhelms all other forces. The laws don't change, but their relative influences shift dramatically based on conditions. As the universe ages, these conditions will continue to evolve. Energy will disperse, matter will decay or transform, space will expand. The relative dominance of different forces and interactions will shift accordingly. Physics as we experience it now exists in a specific cosmic context, one that will not persist eternally. The laws of physics as we currently understand them have been tested primarily in our local region of space, during our brief moment in cosmic history, under the specific conditions available to our experiments. While we have good reason to believe these laws apply universally, we cannot directly verify their behavior under the extreme conditions of the distant cosmic future. What we can do, however, is use our current understanding to project forward, to extrapolate how physics might behave as the universe continues to age. This requires both rigorous application of known principles and speculative imagination about scenarios beyond our direct experience. It is this combination of disciplined analysis and cosmic wonder that will guide our journey through the remaining chapters of our exploration. As we move forward, we will see how the universe transitions through distinct eras, each characterized by different dominant processes and structures. We will observe the strange behavior that emerges as familiar physics encounters unfamiliar conditions. We will witness the transformation of reality itself, as everything we know evolves towards states beyond our ordinary conception. The physics of today's universe provides our foundation, our starting point. From here, we embark on a journey into deep time, where the familiar becomes strange, where certainties dissolve, and where new possibilities emerge from the fading light of cosmic twilight. The stars appear fixed, eternal, unchanging. But this cosmic tapestry constantly transforms, driven by two fundamental processes that will ultimately determine the fate of everything: expansion and entropy. These twin engines of cosmic change operate on different principles but work together to shape the universe's journey from its fiery birth toward its distant future. In 1929, astronomer Edwin Hubble made an observation that would fundamentally alter our understanding of the cosmos. By measuring the light from distant galaxies, he discovered something astonishing. The farther away a galaxy, the faster it appears to be moving away from us. This pattern, now known as Hubble's law, led to a profound revelation, one that contradicted millennia of human intuition. The universe is not static, it expands. This expansion differs from ordinary movement through space. The galaxies are not simply racing away from us through a fixed cosmic backdrop. Rather, space itself stretches, carrying galaxies along like raisins in an expanding loaf of bread. Each raisin moves away from every other raisin as the dough expands. Similarly, in our expanding universe, every galaxy moves away from every other galaxy. There is no special central point from which everything recedes. No matter where in the universe you might find yourself, distant galaxies would appear to be moving away from you. The rate of this expansion, called the Hubble constant, measures how quickly space stretches. Current measurements place its value at approximately 70 kilometers per second per megaparsec. This means that for every megaparsec, about 3.26 million light-years, a galaxy recedes an additional 70 kilometers per second faster. A galaxy 10 megaparsecs away moves away at 700 kilometers per second, while one at 100 megaparsecs recedes at 7,000 kilometers per second. This cosmic expansion has profound implications. It means our universe had a beginning, a moment when all matter and energy existed in an incredibly hot, dense state. This initial condition, what we now call the Big Bang, marked the birth of our universe approximately 13.8 billion years ago. From that moment, space has been stretching, cooling, and evolving into the cosmos we observe today. For decades after Hubble's discovery, physicists debated whether gravity would eventually halt this expansion. After all, every bit of matter in the universe gravitationally attracts every other bit. This mutual attraction should gradually slow the expansion, perhaps eventually causing the universe to contract in what was termed the Big Crunch, a cosmic mirror image of the Big Bang. This scenario would create a cyclical universe, eternally expanding and contracting like a cosmic heartbeat. The evidence gathered since then, however, points in a different direction. In 1998, observations of distant supernovae revealed something unexpected. Not only is the universe expanding, but that expansion is accelerating. Rather than slowing down due to gravity's pull, the expansion rate increases over time. Galaxies move away from each other at ever greater speeds as cosmic time progresses. This acceleration requires an explanation, a force or energy that counteracts gravity's attractive pull. Physicists call this mysterious influence dark energy. Unlike ordinary matter and energy, dark energy exerts negative pressure, effectively pushing space apart rather than pulling it together. The more space expands, the more dark energy it contains, creating a feedback loop of ever-accelerating expansion. Current measurements suggest dark energy constitutes about 68% of the total energy content of the universe. Ordinary matter, the stuff of stars, planets, and living beings, accounts for just 5%. The remaining 27% consists of dark matter, another mysterious substance that interacts gravitationally but does not emit, absorb, or reflect light. Our universe, it seems, is dominated by components we barely understand. The discovery of accelerating expansion fundamentally changed our understanding of cosmic destiny. Rather than eventually contracting, our universe appears destined for endless expansion. This expansion influences cosmic evolution on the grandest scales, determining which processes dominate during different epochs of the universe's history. It also sets the stage for the strange physics that will emerge in the distant future. As expansion continues, galaxies move ever farther apart. Eventually, most will recede from each other faster than light can travel between them. This does not violate Einstein's special relativity, which states that nothing can travel through space faster than light. The galaxies do not move through space at superluminal speeds. Rather, the space between them expands so quickly that their separation increases faster than light can traverse that growing distance. This faster-than-light recession creates a cosmic horizon, a boundary beyond which we can never observe or interact with distant regions, no matter how long we wait. As cosmic time progresses, this horizon shrinks in terms of the number of galaxies it contains. Eventually, in the far distant future, each galaxy cluster becomes an island universe, forever cut off from the rest of the cosmos. Within these isolated clusters, another fundamental process shapes cosmic evolution: entropy. While expansion drives the universe's large-scale structure, entropy governs the flow of energy and the progression of physical processes. Entropy measures disorder or randomness in a system. The second law of thermodynamics states that in closed systems, entropy always increases over time. Order gives way to disorder. Useful energy degrades into unusable heat. Structure eventually dissolves into homogeneity. Imagine a drop of ink falling into a glass of water. Initially, the ink remains concentrated, its molecules ordered in a small volume. Over time, the ink diffuses, spreading throughout the water until it reaches a uniform distribution. This transition from order to disorder exemplifies entropy's increase. Crucially, this process has a direction. While nothing in physics prevents all the ink molecules from spontaneously reassembling into a drop, the probability of such an event occurring is vanishingly small. For all practical purposes, entropy's increase defines time's arrow. In our universe, entropy manifests at all scales. Stars burn through their nuclear fuel, converting organized matter into dispersed radiation. Planets gradually lose their internal heat. Mountains erode. Living organisms maintain their complex structure temporarily by consuming energy and exporting entropy to their surroundings, but eventually succumb to decay. Everything ages, everything weathers, everything eventually dissolves. Yet remarkably, our universe remains far from maximum entropy. If the second law always drives systems toward increasing disorder, why do we observe so much structure? Stars, galaxies, planets, and living beings all represent highly ordered arrangements of matter and energy. The answer lies in the universe's initial conditions and the role of gravity. The early universe contained extreme energy density, but very little entropy. While hot, it was remarkably uniform, with only tiny variations in density from one region to another. These minute fluctuations, seeded by quantum processes during cosmic inflation, provided the starting point for structure formation. Gravity amplified these variations, drawing matter together against entropy's dispersive tendency. Gravity behaves counterintuitively with respect to entropy. When gravity dominates, clumping actually increases entropy. A cloud of gas collapsing to form a star might seem to become more ordered, but the gravitational energy released during collapse converts to heat, vastly increasing the overall entropy of the system. The apparent order of cosmic structures emerges precisely because the universe seeks higher entropy states. This competition between gravity's tendency to create structure and entropy's tendency to dissolve it drives cosmic evolution. In the universe's present era, gravity still holds the upper hand in many contexts. Stars form from interstellar gas, galaxies maintain their shape, planets orbit steadily. But entropy's influence gradually strengthens. Stars exhaust their fuel, galaxies lose stars to intergalactic space, planetary orbits decay through various mechanisms. The accelerating expansion amplifies entropy's effects. As galaxies move beyond each other's cosmic horizons, the accessible energy in the universe decreases. Gravitationally bound structures become increasingly isolated. The usable energy available within each cosmic island diminishes over time. Heat death, a state of maximum entropy where no further useful work can be done, looms in the distant future. Stars represent the universe's primary energy processors, converting the potential energy of matter into radiation through nuclear fusion. Our Sun, a typical main sequence star, fuses hydrogen into helium in its core, releasing energy that sustains life on Earth. This process, while extraordinarily efficient by human standards, remains temporary on cosmic timescales. Eventually, all stars exhaust their nuclear fuel. Our Sun will continue its current stable fusion for approximately another 5 billion years. After that, it will expand into a red giant, briefly fusing helium in its core before shedding its outer layers and leaving behind a white dwarf, a dense ember slowly cooling over trillions of years. More massive stars follow different evolutionary paths, some exploding as supernovae, others collapsing directly into black holes. But regardless of mass, all stars eventually exhaust their ability to generate energy through fusion. New stars continue to form in our present cosmic epoch. Interstellar gas clouds collapse under gravity's influence, their central regions heating until nuclear fusion ignites. But this process depends on available gas, which grows increasingly scarce as existing stars lock matter away in stellar remnants or eject it into intergalactic space. Roughly 1 trillion years from now, the last stars will form from the remaining gas. After that, the universe will host no new stellar births. Existing stars will continue to shine for varying durations. The most massive stars burn out quickly, living only millions of years. Intermediate mass stars like our Sun persist for billions of years. The smallest stars, red dwarfs, sip their hydrogen so slowly that they can continue fusing for trillions of years. But even these cosmic misers, eventually exhaust their fuel. By approximately 100 trillion years from now, the last naturally occurring star will flicker out, marking the end of the stelliferous era, the age of stars. The death of stars dramatically changes the universe's energy landscape. Without fusion power, the cosmos grows increasingly dark and cold. Stellar remnants, white dwarfs, neutron stars, and black holes dominate the galaxy. These dense objects radiate away their remaining thermal energy through various processes, but generate no new heat. The temperature difference between objects and their surroundings, which drives all useful work, gradually diminishes. Yet even in this darkening cosmos, occasional flashes of light punctuate the growing gloom. Stellar remnants sometimes collide, releasing enormous energy in brief outbursts. White dwarfs merging with one another can trigger type Ia supernovae, briefly outshining entire galaxies. Neutron star collisions produce kilonovae, exotic explosions that forge the heaviest elements. Black holes consuming matter emit intense radiation from their superheated accretion disks. These cataclysmic events grow increasingly rare as cosmic time progresses, but continue long after ordinary stellar light has faded. Brown dwarfs, objects too small to sustain hydrogen fusion, slowly cool and contract over trillions of years. Eventually, quantum degeneracy pressure halts their contraction, transforming them into dense, planet-sized black dwarfs. White dwarfs, initially hot from their stellar origins, also cool to this state. These black dwarfs contain substantial carbon, oxygen, and heavier elements created during their previous stellar lives. Though extremely stable, they are not eternal. Over unimaginable timescales, roughly 1 to the power of 1,500 years, quantum tunneling enables protons and neutrons in black dwarfs to overcome their electromagnetic and strong nuclear repulsion and combine. This process, called quantum nucleation, converts ordinary matter into iron, the most stable nuclear configuration. Eventually, black dwarfs transform into cold spheres of iron, their entropy higher than before, but still not maximized. Meanwhile, the expansion of space continues accelerating. Galaxy clusters, the largest gravitationally bound structures, remain intact, held together against cosmic expansion by their immense gravity. But the space between clusters expands faster than light can traverse it. Each cluster becomes entirely isolated, with no possibility of communication or interaction with the broader cosmos. From any vantage point, the observable universe shrinks to encompass only the local galaxy group. Within these isolated clusters, galaxies experience ongoing evolution. They collide and merge, their stars dispersing into a diffuse elliptical distribution. The supermassive black holes at their centers also merge, releasing enormous gravitational wave energy in the process. Eventually, each cluster coalesces into a single enormous galaxy, containing all the matter that once formed many distinct stellar systems. As ordinary stars disappear, the universe grows darker, but not completely dark. Various physical processes produce faint illumination. Black holes accreting matter emit radiation from their surroundings. Particles and antiparticles spontaneously forming in the quantum vacuum briefly annihilate, producing photons. Proton decay, if it occurs, releases energy as subatomic particles break down into lighter components. While dim compared to starlight, these sources provide the only remaining electromagnetic radiation in an increasingly dark cosmos. Dark matter, the mysterious substance that currently constitutes most of the universe's mass, plays an important role in this era. Unlike ordinary matter, dark matter does not form atoms or complex structures. It interacts primarily through gravity, forming extensive halos around galaxies. As ordinary matter concentrates through collisions and other dissipative processes, dark matter remains more diffusely distributed. Its gravitational effects help hold cosmic structures together, even as other forces drive them apart. The fate of dark matter itself remains uncertain, as we have not conclusively identified its nature. If composed of stable particles, it might persist indefinitely, eventually becoming the dominant form of matter as ordinary protons and neutrons decay. If unstable, albeit with an extremely long lifetime, dark matter might eventually decay into radiation, contributing to the universe's entropy increase. Black holes become increasingly important as cosmic time progresses. These objects, regions of space-time where gravity is so intense that nothing, not even light, can escape, represent the most concentrated form of matter in the universe. Stellar mass black holes form from collapsed stars. Supermassive black holes, millions or billions of times more massive than our Sun, reside at galaxy centers. Primordial black holes, if they exist, formed directly during the early universe from density fluctuations. Through various processes, black holes grow by consuming surrounding matter and merging with one another. The supermassive black holes at galaxy centers absorb stars that venture too close. Stellar mass black holes occasionally capture their companions in binary systems. Over vast timescales, dynamical friction causes black holes to sink toward galactic centers, increasing the likelihood of mergers. These processes gradually convert an increasing fraction of each galaxy's mass into black holes. However, black holes do not represent the universe's final state. In 1974, physicist Stephen Hawking made a remarkable discovery. When quantum effects are considered, black holes are not truly black. They emit radiation, now called Hawking radiation, with a temperature inversely proportional to their mass. Larger black holes remain extremely cold, emitting negligible radiation. But as they lose mass through this process, they grow hotter, radiating more intensely in a feedback loop that eventually leads to their complete evaporation. A stellar mass black hole takes approximately 10 to the power of 67 years to evaporate completely, far longer than the current age of the universe. Supermassive black holes persist even longer, up to 10 to the power of 100 years. But even these immense durations are finite on the scale of cosmic time. Eventually, all black holes disappear, converting their mass entirely to radiation and raising the universe's entropy to ever higher levels. By the time black holes finish evaporating, roughly 10 to the power of 100 years from now, the universe will have changed beyond recognition. No stars shine, no planets orbit, no complex matter structures exist. Protons and neutrons have likely decayed into lighter particles. Black holes have converted their mass to radiation. All that remains are elementary particles, separation distances growing ever larger due to cosmic expansion, and a dilute soup of photons and other radiation, gradually cooling toward absolute zero. This progression toward disorder might seem depressing, a cosmic tale of decline and decay, but entropy's increase enables all the complexity we observe. Without thermodynamic gradients, no work can be done, no information processed, no life sustained. The flow from order to disorder powers everything from photosynthesis to human thought. Entropy produces complexity on the path to equilibrium, like a river carving intricate landscapes as it flows inevitably toward the sea. Entropy also connects intimately with information. In the 1940s, physicist Claude Shannon formalized this relationship, showing that entropy quantifies the information content of a system. High entropy states contain more information than low entropy states, precisely because they have more possible arrangements. Paradoxically, as the universe's physical entropy increases, its information content also increases, though this information becomes increasingly difficult to access or utilize. The universe we inhabit exists in a middle state, neither completely ordered nor completely disordered. This intermediate position enables complexity. If the cosmos were already at maximum entropy, no structure could exist, no processes could occur, no life could think. If it were at minimum entropy, crystalline perfection would preclude the variations necessary for complex systems. Our existence depends on the universe's journey from order to disorder, not on either extreme state. As entropy increases and expansion accelerates, the nature of physics itself changes. Different laws and principles dominate during different cosmic eras. The physics of black hole evaporation, proton decay, and quantum fluctuations in vacuum, currently minor footnotes in textbooks, become the primary processes in the far future. The relative importance of forces shifts dramatically. What seems fundamental today may appear transient from the perspective of deep time. This shifting dominance raises profound questions. Are the laws of physics themselves subject to change? Do fundamental constants drift over cosmic timescales? Might entirely new physical principles emerge under the extreme conditions of an aging universe? These questions guide our continuing journey into cosmic deep time as we explore the strange behavior of physics at the end of the universe. The marriage of expansion and entropy carries our cosmos toward a state profoundly different from its present configuration. Yet this journey is not simply one of loss, it is one of transformation. As familiar structures fade, new possibilities emerge. Physics reveals new behaviors in extreme conditions. Information reconfigures into novel patterns. The cosmic story continues, following different principles, operating at different scales, but never truly ending. As we venture deeper into cosmic time in the chapters ahead, we will explore more exotic phenomena. The dominance of black holes, the decay of ordinary matter, the strange behavior of time itself in a nearly empty universe. These topics await us. The universe's expansion and entropy increase set the stage for these transformations, creating the conditions where conventional physics gives way to its stranger manifestation. None twist the fabric of reality more profoundly than black holes. These extraordinary entities, where matter has collapsed to infinite density, create boundaries in space-time, where conventional physics breaks down and time itself behaves in ways that challenge our deepest intuitions. In the far future of our universe, as stars burn out and matter decays, black holes will dominate the cosmic landscape, becoming the primary sculptors of reality before they too succumb to quantum processes that reveal new facets of fundamental physics. A black hole forms when matter compresses so densely that nothing, not even light, can escape its gravitational pull. The boundary marking this point of no return is called the event horizon, a spherical surface that acts as a one-way membrane. Information can enter but never leave. This profound asymmetry creates what physicists call an information paradox, a contradiction between quantum mechanics, which forbids information destruction, and the apparent loss of information when matter falls into a black hole. The conventional narrative of a black hole begins with stellar death, when a sufficiently massive star, at least 8 times the mass of our Sun, exhausts its nuclear fuel. Its core collapses catastrophically. The outer layers explode in a supernova, while the core implodes, its protons and electrons merging to form neutrons. If the core exceeds about 3 solar masses, even the quantum pressure of neutrons cannot halt the collapse. Space-time curves so severely that a black hole forms, its mass concentrated at a central point called the singularity, where density becomes infinite and known physics breaks down. While stellar collapse represents the most common black hole formation mechanism in our current cosmic epoch, other processes create these extreme objects. Galaxy centers host supermassive black holes millions or billions of times more massive than our Sun. Our own galaxy, the Milky Way, contains a 4 million solar mass black hole called Sagittarius A star at its center. These behemoths likely grew from smaller seed black holes that merged with others and consumed surrounding matter over billions of years. Some theoretical models suggest the early universe might have created primordial black holes directly from density fluctuations moments after the Big Bang. These could range from microscopic masses to thousands of solar masses. While not yet confirmed observationally, such primordial black holes could contribute to dark matter and seed the growth of larger black holes. Regardless of their origin, all black holes share certain fundamental properties. Each is characterized by just 3 parameters: mass, electric charge, and angular momentum, or spin. This simplicity, often summarized by the phrase, "black holes have no hair," means that all other information about the matter that formed the black hole appears lost. A black hole formed from hydrogen looks identical to one formed from iron or exotic matter. This erasure of information creates profound theoretical puzzles. The event horizon, that boundary beyond which escape becomes impossible, represents a special surface in space-time. While nothing dramatic happens to an observer crossing this threshold, it marks a fundamental change in causal structure. Inside the horizon, all future world lines, all possible paths through space-time, lead inexorably toward the central singularity. The radial direction effectively becomes time-like rather than space-like. Just as we cannot avoid moving forward in time, an entity inside the event horizon cannot avoid moving toward the singularity. From an outside perspective, time behaves strangely near a black hole. As a clock approaches the event horizon, its ticking appears to slow relative to distant observers, an effect called gravitational time dilation. A clock falling into a black hole would appear to freeze at the horizon, its final tick stretched across eternity. Meanwhile, light from the falling clock redshifts to longer wavelengths, eventually becoming undetectable. From the perspective of someone falling into a black hole, however, time passes normally. The event horizon has no local significance, appearing as just another region of space. Only by communicating with distant observers, an impossible task once inside the horizon, would the falling person recognize their special location. This disconnect between local and global perspectives highlights a crucial insight from general relativity. Time is not absolute, but relative to the observer's state of motion and gravitational potential. Black holes do not merely warp time, they curve space itself into configurations difficult to visualize. Imagine space as a two-dimensional rubber sheet. A marble creates a shallow depression, representing Earth's gravitational field. A bowling ball creates a deeper well, like a star. A black hole stretches the sheet infinitely downward, forming a bottomless funnel. This spatial curvature redirects the paths of objects and light rays, creating phenomena like gravitational lensing, where distant light sources appear distorted or multiply imaged. Rotating black holes exhibit even stranger properties. Their spin drags space-time around them, a phenomenon called frame dragging. Close to a rapidly spinning black hole, space itself rotates at nearly the speed of light. This rotation creates a region called the ergosphere, where nothing can remain stationary relative to distant space. Even light must orbit in the same direction as the black hole's spin when in this region. The ergosphere enables a process called superradiance, where waves scattered by the black hole can extract some of its rotational energy. These peculiar space-time geometries allow for exotic possibilities. Certain solutions to Einstein's equations suggest rotating black holes might contain closed time-like curves, paths through space-time that return to their starting point in time, effectively enabling time travel. Other solutions propose wormholes, theoretical tunnels connecting distant regions of space-time. While mathematically valid, such solutions typically require exotic negative energy or negative mass to remain stable, substances not known to exist naturally. The central singularity, where matter compresses to infinite density, represents a breakdown of general relativity itself. The theory predicts its own failure here, as quantum effects become crucial at such extreme scales. Many physicists believe a complete theory of quantum gravity will resolve the singularity, replacing it with something less pathological. Until we develop such a theory, the singularity remains a boundary of current physical understanding, a place where time as we understand it ceases to have meaning. Stephen Hawking's seminal work in the 1970s revealed that black holes are not entirely black. Quantum mechanics requires virtual particle pairs to continuously pop into existence throughout space, normally annihilating almost instantly. Near an event horizon, however, one particle might fall in, while the other escapes, effectively stealing energy from the black hole's gravitational field. This process, called Hawking radiation, causes black holes to slowly evaporate, their mass converting to radiation over immense timescales. The temperature of this radiation inversely relates to the black hole's mass. A stellar mass black hole radiates at less than a millionth of a degree above absolute zero, far colder than the current cosmic microwave background. Such black holes currently absorb more energy from this background radiation than they emit, actually growing rather than evaporating. Only when the universe cools below their radiation temperature will they begin to shrink. As a black hole loses mass through Hawking radiation, its temperature rises, accelerating the evaporation process. The final moments become explosive, with the remaining energy released in a burst of high-energy particles. A black hole with the mass of our Sun would take approximately 10 to the power of 67 years to evaporate completely. Supermassive black holes might persist for up to 10 to the power of 100 years. These durations vastly exceed the current age of the universe, but remain finite on the scale of cosmic time. The very existence of Hawking radiation transformed our understanding of black hole thermodynamics. Black holes possess entropy, a measure of disorder or information content, proportional to their surface area. A stellar mass black hole has entropy roughly equivalent to 10 to the power of 77 bits of information, vastly exceeding the entropy of the star from which it formed. This enormous information capacity suggests black holes represent the most efficient information storage mechanism allowed by physics. This thermodynamic perspective raises profound questions about information and its preservation. If matter falling into a black hole carries information about its state, and the black hole eventually evaporates into seemingly random thermal radiation, what happens to that information? Does it truly vanish, violating a fundamental principle of quantum mechanics? Or does it somehow encode itself in subtle correlations among the emitted particles? This black hole information paradox remains one of the most significant unsolved problems in theoretical physics. Recent developments suggest the information paradox connects to quantum entanglement, the phenomenon Einstein called spooky action at a distance. Particles inside and outside a black hole may remain entangled, preserving correlations that encode information. The holographic principle, a revolutionary concept emerging from string theory, proposes that all information within a volume of space can be represented on its boundary surface. Applied to black holes, this suggests the event horizon itself might store all information about the interior, resolving the paradox. In the cosmic far future, as stars exhaust their fuel and dissipate their energy, black holes become increasingly dominant features of the universe. During what cosmologists call the black hole era, extending from approximately 10 to the power of 40 to 10 to the power of 100 years from now, these objects become the primary energy sources and governing influences on cosmic evolution. Several processes contribute to black hole dominance during this era. Stellar remnants occasionally collide, forming new black holes. Existing black holes consume surrounding matter and occasionally merge with one another. Quantum tunneling allows extremely dense objects like neutron stars to spontaneously collapse into black holes. Through these mechanisms, an increasing fraction of the universe's remaining matter concentrates in black holes of various sizes. Within each isolated galaxy cluster, complex gravitational interactions occur over incomprehensibly long timescales. Stars and stellar remnants exchange energy through close encounters, a process mathematicians call the gravitational n-body problem. These interactions gradually eject some objects into intergalactic space, while causing others to spiral toward the central supermassive black hole. Over periods of 10 to the power of 20 years or longer, many stars and smaller black holes are consumed by the supermassive black hole at each galaxy's center. As black holes consume matter, they convert roughly 10% of its rest mass to energy, released as heat, light, and other radiation from the superheated accretion disk that forms around them. This process, though extraordinarily efficient compared to nuclear fusion, which converts less than 1% of mass to energy, occurs rarely in the far future due to the scarcity of available matter. When it does happen, these accretion events provide brief flashes of light in an increasingly dark cosmos. Black holes also emit gravitational waves when they orbit one another or merge. These ripples in spacetime carry away energy and angular momentum, causing orbiting black holes to gradually spiral together. The final merger releases enormous energy, converting up to several percent of the combined mass to gravitational radiation in a brief moment. In the far future, such mergers represent some of the most energetic events in the universe, though they occur with decreasing frequency as the available supply of black holes diminishes. During the black hole era, these objects not only dominate the mass distribution, but also become the primary information processors in the cosmos. The physicist Seth Lloyd has calculated that black holes represent the ultimate computing devices, their event horizons, processing information at the maximum rate allowed by fundamental physics. The total information processing capacity of a black hole exceeds that of any conventional computer by an astronomical factor. This perspective suggests black holes might support complex dynamics analogous to computation or thought, operating at extremely slow rates relative to human timescales. While highly speculative, such information processing could theoretically enable consciousness, like phenomena, in suitably complex black hole systems. The physicist Roger Penrose has proposed that quantum gravitational effects in black holes might support forms of awareness fundamentally different from biological consciousness, but sharing certain essential characteristics. As black holes slowly evaporate through Hawking radiation, they release their stored information back into the universe. Initially, this radiation consists primarily of photons, gravitons, and other massless particles. During the final stages of evaporation, When the black hole shrinks to microscopic size, it produces a broader spectrum of particles, potentially including massive entities like electrons and quarks. The final explosion, though energetic on human scales, represents a tiny event in the context of the cold, vast universe of that distant era. By approximately 10 to the power of 100 years after the Big Bang, even the largest supermassive black holes complete their evaporation. The universe enters what cosmologists call the dark era, a period of extremely low energy and maximized entropy. No black holes remain, no stars shine. Even protons and neutrons have long since decayed, if they are indeed unstable, as many theories predict. The universe consists primarily of photons, neutrinos, electrons, positrons, and dark matter particles, all separated by enormous and continuously expanding distances. During the black hole era, these extraordinary objects not only dominated the physical landscape, but also transformed our understanding of fundamental physics. Their evaporation through Hawking radiation demonstrated the deep connection between gravity, quantum mechanics, and thermodynamics. Their information processing capacity illuminated the relationship between physical systems and computation. Their eventual disappearance marked a transition to yet another cosmic epoch, one governed by even stranger physics. The humble black hole, once considered a mathematical curiosity, unlikely to exist in nature, emerged as perhaps the most important physical system for understanding the universe's ultimate fate. In these cosmic crucibles, where space-time curves back upon itself and conventional notions of before and after lose meaning, physicists found crucial clues about the nature of time itself. Throughout this narrative, we have described time as something that flows, that passes, that moves forward. But this intuitive picture becomes problematic near black holes, where different observers disagree about the timing and sequence of events. General relativity teaches us that time is not absolute but relative, woven together with space into a unified fabric that curves in response to matter and energy. At a black hole's event horizon, this relativistic perspective reveals its full implications. A distant observer never sees anything cross the horizon, while someone falling in experiences nothing special at crossing. The same moment appears radically different depending on one's reference frame. These disagreements cannot be resolved by better communication or more careful measurement. They reflect fundamental properties of space-time itself. Even more profoundly, certain solutions to Einstein's equations, like the interior of rotating black holes, contain regions where the very distinction between space and time breaks down. Coordinates that represent spatial dimensions outside the black hole become temporal ones inside, and vice versa. The mathematical structure remains continuous, but the physical interpretation changes dramatically, suggesting that space and time may be two aspects of a more fundamental entity, rather than distinct concepts. Some theoretical approaches to quantum gravity even suggest that time itself may be emergent rather than fundamental. Just as temperature emerges from the collective motion of atoms rather than being a fundamental property of individual particles, time might emerge from deeper quantum gravitational processes, rather than representing a basic feature of reality. Black holes, where quantum gravity effects become crucial near the singularity, provide our best opportunity to explore such possibilities. The breakdown of conventional time near black holes mirrors what may happen to the universe as a whole in the far distant future. As everything grows cold, dark, and diffuse, as entropy approaches its maximum, as energy gradients disappear, change itself becomes increasingly rare. In such a state, with nothing to mark temporal progression, does time retain meaning? Can we speak of before and after when nothing happens to distinguish one moment from another? These questions lead us toward profound philosophical territory as much as physical. The strange behavior of time under extreme conditions suggests our everyday experience of time's flow might be provincial, a perspective limited by our particular circumstances, rather than reflecting time's fundamental nature. Just as pre-relativistic physics mistakenly assumed absolute simultaneity, our intuitive sense of time passing might represent a limited perspective that breaks down under sufficient scrutiny. As we journey deeper into cosmic time in the coming chapters, these questions about time's nature will recur with increasing urgency. The physics that emerges at the end of the universe challenges not only our understanding of matter and energy, but our very conception of when and how events occur. The breakdown of conventional time might represent not an ending, but a transition to something even more fundamental, something glimpsed only fleetingly in the extreme physics of black holes. What we learn from black holes extends far beyond their specific properties. These extraordinary objects teach us that time, space, information, energy, and entropy interconnect in ways that conventional physics only partially captures. The strange behavior of black holes foreshadows the strange behavior of the universe itself in its final stages. By understanding these cosmic singularities, we gain insight into the ultimate singularity, the end state toward which our entire cosmic time. When stars have burned out and black holes have evaporated, the universe enters a phase dominated by processes so subtle they are practically undetectable in our present era. These quantum fluctuations, tiny ripples in the fabric of reality itself, become the primary drivers of physical change. In this vastly dilute cosmos, where matter is scarce and conventional energy sources exhausted, everything we consider stable and permanent reveals its temporary nature. Even the seeming emptiness of space contains the seeds of creation and destruction, operating on timescales that dwarf our current cosmic age. Quantum mechanics, our framework for understanding reality at the smallest scales, tells us that empty space is never truly empty. The vacuum, rather than being a void of nothingness, seethes with activity at the quantum level. The Heisenberg uncertainty principle, a cornerstone of quantum theory, prevents any region of space from having exactly zero energy for any extended period. Instead, the vacuum constantly produces virtual particles that pop briefly into existence before disappearing again. These virtual particles emerge in pairs, a particle and its corresponding antiparticle. An electron pairs with a positron, a quark with an antiquark, a photon with another photon. These partners materialize from the vacuum, exist for an infinitesimal moment, then reunite and annihilate, returning their borrowed energy to the void. The briefer their existence, the more energy they can borrow, according to the time-energy uncertainty relation. This continuous creation and destruction of particles generates what physicists call quantum fluctuations, a background froth of activity underlying all of reality. In our present epoch, these vacuum fluctuations have observable consequences. The Casimir effect, where parallel plates placed extremely close together experience a small, attractive force, demonstrates the reality of virtual particles. The plates restrict which fluctuations can form in the narrow gap between them, creating a pressure difference that pushes them together. Similarly, the Lamb shift, a small difference in energy levels in hydrogen atoms, results from interactions between electrons and virtual photons emerging from the vacuum. Quantum fluctuations played a crucial role in the early universe. During cosmic inflation, the exponential expansion in the first fraction of a second after the Big Bang, quantum fluctuations stretched to macroscopic scales. These tiny variations in energy density provided the seeds for future structure formation, the regions where matter would eventually concentrate to form galaxies and galaxy clusters. The entire cosmic web of matter that defines our observable universe originated from quantum-scale randomness, amplified by inflation and gravity. In our universe's far future, quantum fluctuations again become dominant, but in a very different context. With stars extinguished, black holes evaporated, and matter dispersed or decayed, conventional physics gives way to quantum processes operating over enormous timescales. The primary action in this cold, dark cosmos occurs through tunneling, fluctuations, and other quantum effects that would be practically unobservable in our current environment. Consider the true vacuum state, the lowest possible energy configuration of empty space. Our current understanding suggests the vacuum we observe might not represent this true minimum. Like a ball resting in a shallow depression partway up a hill rather than at the bottom, our vacuum could be metastable rather than absolutely stable. If this is the case, a quantum fluctuation could potentially trigger a transition to a lower energy state, fundamentally altering the physical laws throughout the affected region. Such a vacuum decay would create a bubble of new vacuum that expands at nearly the speed of light. Inside this bubble, the fundamental constants, particle masses, and interaction strengths might differ dramatically from our familiar physics. The energy released in this transition would briefly create conditions resembling the early universe, potentially enabling new structures to form. From our perspective, such a transition would be catastrophic, instantly destroying everything in its path. But in the context of eternity, it might represent just another phase in cosmic evolution. The probability of such a vacuum decay occurring in any given volume of space is extraordinarily small, estimated at less than 1 in 10 to the power of 100 per cubic meter per second. But given infinite time, even the most improbable events eventually occur. Some calculations suggest a vacuum decay becomes virtually inevitable over timescales of 10 to the power of several hundred years. While incomprehensibly distant by human standards, this remains finite in the context of cosmic eternity. This concept of metastability extends to many physical systems. Protons, the building blocks of atomic nuclei, appear completely stable based on current observations. No confirmed proton decay has ever been recorded, placing the proton lifetime at greater than 10 to the power of 34 years. But many grand unified theories, which attempt to unify the electromagnetic, weak, and strong nuclear forces, predict that protons must eventually decay, transforming into lighter particles and releasing energy. If protons do decay, all conventional matter becomes unstable over sufficiently long timescales. Atomic nuclei would gradually disintegrate, leaving behind radiation and elementary particles. Complex structures, from molecules to planets to black holes, would eventually dissolve into their fundamental constituents. The time required for this process extends far beyond the current age of the universe, but remains finite. In the extreme future, no complex matter would remain, regardless of how stable it appears from our present perspective. The universe in this era would consist primarily of photons, neutrinos, electrons, positrons, and perhaps stable dark matter particles, all separated by enormous and continuously increasing distances due to cosmic expansion. Occasionally, an electron and positron might meet and annihilate, producing gamma rays that travel eternally through the vast emptiness, rarely encountering anything. The universe approaches but never quite reaches a state of perfect equilibrium, maximum entropy, and complete uniformity. However, this progression toward disorder can temporarily reverse through random fluctuations. The physicist Ludwig Boltzmann recognized that in any system, entropy can spontaneously decrease through random chance, though the probability diminishes exponentially with the magnitude of the decrease. Given sufficient time, even highly ordered states can emerge randomly from disorder, though they quickly dissolve again. This concept, formalized as Boltzmann brains, suggests that over infinite time, conscious entities might spontaneously form from quantum fluctuations, exist briefly, then dissipate. Such fluctuations need not be limited to small systems. In principle, quantum effects could produce arbitrarily large and complex structures, including entire solar systems, galaxies, or even regions resembling our observable universe. The probability of such events decreases exponentially with their scale and complexity, but never reaches exactly zero. On timescales beyond 10 to the power of 10 to the power of 100 years, fluctuations might create structures comparable to those we observe today, brief islands of order in an ocean of entropy. These processes illustrate a profound insight. In a universe governed by quantum mechanics and existing for infinite time, nothing is truly impossible, merely improbable. Events with non-zero probability must eventually occur if we wait long enough. This principle applies not only to random fluctuations, but to tunneling processes, where quantum entities traverse energy barriers that would be insurmountable, according to classical physics. Quantum tunneling enables particles to appear where classical mechanics forbids them. An electron bound in an atom can tunnel through the electric potential barrier and escape. A proton in an atomic nucleus can tunnel through the nuclear force barrier, enabling certain types of radioactive decay. At even higher energy barriers, quantum tunneling allows transmutation of elements, fusion reactions in stars, and potentially the creation of microscopic black holes from concentrated energy. In the cold, diffuse cosmos of the far future, tunneling becomes one of the primary mechanisms for change. Elementary particles tunnel through vast distances to interact with one another. Vacuum fluctuations tunnel between different energy states. Remnant black holes tunnel into alternative configurations before their final evaporation. These processes occur with vanishingly small probability in any given moment, but over the effectively infinite time available in cosmic deep future, they shape the evolution of what remains. Modern physics suggests even space-time itself might exhibit quantum behavior at sufficiently small scales or under appropriate conditions. While we lack a complete theory of quantum gravity, various approaches indicate space and time might not be continuous but discrete at the Planck scale, about 10 to the negative 35 meters. At this scale, space-time could resemble a quantum foam with tiny wormholes, virtual black holes, and topological fluctuations constantly forming and dissolving. These space-time fluctuations, negligible under ordinary conditions, potentially become significant in the far future universe where little else happens. They might enable matter and energy to tunnel between distant regions, temporarily violating conservation laws through quantum borrowing. They could create microscopic regions where time briefly runs backward, entropy momentarily decreases, or additional spatial dimensions temporarily manifest. The boundaries between possible and impossible blur at these scales and timescales. The quantum nature of reality introduces a profound indeterminism into cosmic evolution. Unlike classical physics, where identical initial conditions always produce identical outcomes, quantum systems involve fundamental randomness. This indeterminism prevents us from precisely predicting the future state of the universe, even in principle. The cosmic history becomes a branching tree of possibilities, rather than a single predetermined path. This quantum indeterminism relates to the many worlds interpretation of quantum mechanics, proposed by physicist Hugh Everett in the 1950s. This framework suggests that all possible outcomes of quantum measurements occur, but in different branches of an ever-splitting universal wave function. Rather than a single universe evolving along one trajectory, reality comprises a vast multiverse of possibilities, constantly branching like an infinite tree. If the many worlds interpretation accurately describes reality, the far future contains not one fate but countless variations. In some branches, vacuum decay occurs relatively soon. In others, it never happens. Some branches see novel structures emerge from quantum fluctuations, while others remain forever empty. The full cosmic story encompasses all these possibilities simultaneously, weaving them into an inconceivably complex tapestry of potential realities. Beyond known quantum effects lie speculative processes that might operate in the deep future. Some theoretical approaches suggest that in an infinitely expanding universe, quantum fluctuations could spontaneously create new inflationary regions, essentially birthing baby universes disconnected from our own. These daughter cosmos would expand into their own spaces, potentially developing their own physical laws and constants, unreachable and unobservable from our region. Similarly, certain formulations of string theory propose the existence of a vast landscape of possible vacuum states, each with different physical laws. Quantum tunneling might enable transitions between these states over enormous timescales. Our observable universe would represent just one temporary configuration in an eternal process of vacuum state transitions, each lasting inconceivably long by human standards, but finite in the context of eternal cosmic evolution. These exotic possibilities highlight a recurring theme in our exploration of cosmic deep time. What seems permanent from our perspective often proves temporary when viewed across sufficiently long durations. Stars, once thought eternal by ancient astronomers, burn for merely billions or trillions of years. Atoms, considered indivisible by early scientists, eventually decay over timescales of 10 to the power of 30+ years. Even the vacuum itself, apparently unchanging, harbors the potential for sudden dramatic transformation. This revelation of impermanence applies not only to physical structures, but to the laws of physics themselves. What we call physical laws may represent not timeless truths, but lengthy phases in cosmic evolution. As conditions change dramatically over sufficiently long timescales, different laws may become relevant, or existing laws may manifest in radically different ways. The physics governing an expanding, cooling universe dominated by quantum fluctuations differs fundamentally from the physics of our current era. Consider the transition from quantum to classical behavior. In our everyday experience, quantum effects remain largely invisible, relevant only at atomic and subatomic scales. Classical physics adequately describes most macroscopic phenomena, But this boundary between quantum and classical is not absolute. Under appropriate conditions, quantum behavior can manifest at larger scales, as demonstrated by superfluidity, superconductivity, and Bose-Einstein condensates. In the far future universe, with its extreme emptiness, cold temperatures, and absence of decoherence-inducing interactions, quantum effects might extend to much larger scales than currently possible. Macroscopic objects, if any still existed, could potentially exhibit wave-like properties, tunneling, or superposition states that would seem miraculous by today's standards. The quantum classical boundary shifts depending on environmental conditions. Similarly, the distinction between matter and energy blurs under extreme conditions. Einstein's famous equation, E equals mc squared, established their equivalence, but in our ordinary experience, matter and energy appear quite distinct. In the early universe's extreme heat, or near black holes, or during high-energy particle collisions, this distinction breaks down. Matter readily converts to energy, and vice versa. In the far future, with ordinary matter decayed and energy dispersed, the remaining particles exist in a state where this distinction loses practical meaning. The decay processes we've discussed illuminate another important principle. Conservation laws, though seemingly absolute, include subtle exceptions under appropriate conditions. Energy conservation appears to be violated by vacuum fluctuations, though only temporarily and within the constraints of the uncertainty principle. Baryon number conservation, which would prevent proton decay, can be violated by certain grand unified theory processes. Even space-time symmetries, which generate conservation laws according to Noether's theorem, might break under quantum gravity effects. These exceptions do not invalidate the conservation principles that form the foundation of physics. Rather, they reveal their conditional nature, their dependence on specific circumstances and scales. Just as Newtonian mechanics gives way to relativity at high speeds, but remains valid in everyday situations, conservation laws may have domains of applicability beyond which more fundamental principles take precedence. The gradual decay of everything through quantum processes raises profound questions about information. If all structures eventually dissolve into elementary particles, and these particles themselves transform or disperse, what happens to the information they contained? Does the specific arrangement of atoms in a DNA molecule, or neurons in a brain, or words in a book leave any permanent trace after quantum decay processes complete? The holographic principle, emerging from studies of black hole thermodynamics, suggests information cannot be truly destroyed in a quantum universe. Instead, it becomes encoded in increasingly subtle correlations between particles, spreading throughout the cosmos, but never vanishing entirely. Like a hologram, where each fragment contains information about the whole image at lower resolution, the universe preserves information by distributing it non-locally across vast regions. This preservation of information connects to quantum entanglement, the phenomenon Einstein called spooky action at a distance. Particles that interact become entangled, their properties correlated regardless of the distance separating them. As particles interact and disperse throughout the expanding universe, they create an intricate web of entanglement. This quantum network encodes the history of all previous interactions, a cosmic memory that persists even as local structures decay. Physicist Seth Lloyd has proposed viewing the universe itself as a quantum computer, constantly processing information through particle interactions. From this perspective, cosmic evolution represents an ongoing computation of unimaginable complexity. The decay of structures and dispersal of particles corresponds not to information loss, but to information processing, the universe computing its own future state from its present configuration. This computational metaphor suggests the seemingly empty cosmos of the far future continues to process information, albeit at ever-decreasing rates as interactions become rarer. The universe computes ever more slowly as it cools and expands, but the computation never entirely ceases. Quantum fluctuations ensure some minimal level of information processing continues indefinitely, maintaining the cosmic calculation across eternity. These fluctuations in the quantum vacuum relate to another remarkable phenomenon, the creation of particles from seemingly nothing. In 1974, Stephen Hawking shocked the physics community by demonstrating that black holes emit radiation, effectively converting their mass back into particles. This process, now called Hawking radiation, results when virtual particle pairs form near the event horizon, with one partner falling in, while the other escapes. A similar process can occur in rapidly expanding or contracting spacetime. Known as cosmological particle creation, this phenomenon played an important role during cosmic inflation, when the universe's exponential expansion converted vacuum energy into the hot plasma of the Big Bang. In principle, the continuing acceleration of cosmic expansion could create particles through an analogous mechanism, though at an extraordinarily slow rate in the present era. Even in flat, static spacetime, quantum field theory permits the spontaneous materialization of particle pairs in strong electromagnetic fields. This phenomenon, called the Schwinger effect, occurs when the electric field reaches a critical value, providing enough energy to convert vacuum fluctuations into real particles. While difficult to achieve experimentally, these processes demonstrate that the boundary between vacuum and matter remains permeable, allowing transformation in both directions under appropriate conditions. The vacuum itself can be understood as a complex, structured entity, rather than simple nothingness. Quantum field theory describes the vacuum as the lowest energy state of quantum fields, which permeate all of spacetime. These fields, such as the electromagnetic field, the electron field, and others for every type of elementary particle, exist everywhere, even in the absence of particles. Particles represent excitations of these underlying fields, like waves on the surface of an ocean. This field perspective illuminates why particles can emerge from and return to the vacuum. When a quantum of energy excites a field, a particle appears. When that energy dissipates, the particle vanishes. The vacuum contains the potential for all possible particles, a sea of possibility from which reality continuously manifests and into which it dissolves. In the far future universe, as conventional matter decays, this quantum potential remains, ensuring the cosmos never reaches absolute emptiness. The quantum vacuum, with its fluctuations and virtual particles, highlights a profound philosophical principle: nothingness, in any absolute sense, may be impossible. Even the most perfect vacuum permitted by physical law contains energy, structure, and potential. True nothingness, the complete absence of fields, space, time, and possibility, appears prohibited by quantum mechanics. Something, however minimal, must always exist. This insight transforms our understanding of the universe's far future. Rather than ending in absolute emptiness, cosmic evolution continues indefinitely through quantum processes of incomprehensible subtlety. The universe never reaches perfect equilibrium or complete uniformity. Quantum indeterminism ensures fluctuations always occur, creating brief, rare islands of structure in an ocean of near-nothingness. As we contemplate these quantum processes and their implications for cosmic deep time, we confront not just the outer boundaries of physics, but the limits of human comprehension itself. The timescales involved, the extreme conditions, the counterintuitive quantum behaviors, all challenge our intuition, which evolved to navigate the macroscopic world of moderate energies and timescales. Yet mathematics and theoretical physics allow us to explore these realms conceptually, extending our understanding beyond direct experience. The picture that emerges depicts a universe of profound impermanence, where everything we consider solid and enduring eventually dissolves. Yet within this impermanence lies a strange form of eternity. The quantum vacuum, with its fluctuations and potential, persists indefinitely. Information, though dispersed and transformed, remains encoded in quantum correlations. The fundamental fields that comprise reality continue to exist, even as their excitations shift and fade. This tension between transience and persistence, between decay and renewal, characterizes the quantum universe at the end of time. Nothing lasts forever in its present form, yet nothing disappears completely. Everything transforms, cycling between manifestation and potentiality across timescales that dwarf our cosmic age. The strange behavior of physics in this ultimate epoch reveals not an ending, but a transformation, not death, but metamorphosis. As the universe continues its eternal dance, the laws of physics as eternal and unchanging, mathematical truths that govern reality across all space and time. The gravitational constant, the speed of light, the charge of an electron, the strength of the nuclear forces, these values appear fixed, immutable pillars upon which our understanding of the universe rests. But what if this perspective represents merely a limited view, constrained by our brief cosmic moment? What if the laws themselves evolve over the vast stretches of deep time, changing gradually as the universe ages, or manifesting differently under the extreme conditions of cosmic twilight? This question challenges our most fundamental assumptions about reality. The very concept of physical law presupposes consistency, reliability, predictability. Yet as we venture into the far future, as we contemplate timescales that dwarf the current age of the universe, we must consider the possibility that what we call laws might better be understood as phases, as temporary patterns in an evolving cosmos, as rules that themselves transform across sufficient duration. The concept of evolving physical laws appears in various theoretical frameworks. The most conservative approach suggests the fundamental constants of nature might drift slightly over enormous timescales. These constants include values like the fine structure constant, which governs electromagnetic interactions, the gravitational constant, which determines gravity's strength, and the cosmological constant, which drives the universe's accelerated expansion. While currently appearing fixed, these values might change imperceptibly slowly, their evolution noticeable only across billions or trillions of years. Several observations and theories support this possibility. Some analyses of light from distant quasars suggest the fine structure constant might have been slightly different billions of years ago, though these results remain contentious. String theory, a candidate for unified physics, naturally produces a vast landscape of possible vacuum states, each with different physical constants. If our universe can transition between these states, the constants might jump discretely at certain moments or gradually drift as the cosmic environment evolves. Even more intriguing is the anthropic explanation for the apparent fine-tuning of physical constants. Our universe's parameters seem precisely calibrated to allow complexity and life. Slight changes to the strength of the nuclear force, the electron mass, or dozens of other values would create a universe without stars, atoms, or chemistry as we know it. This extraordinary coincidence might indicate we observe these particular values precisely because they permit observers to exist. In a vast multiverse with regions governed by different constants, only those regions compatible with life would contain beings capable of measuring those constants. If the multiverse theory holds true, and if transitions between different physical regimes can occur, then the laws governing our cosmic patch might indeed evolve. Just as biological evolution produces organisms adapted to their environment, cosmic evolution might naturally select for regions with physical laws conducive to complexity and structure formation. Our observed laws would represent not unique, eternal truths, but the current configuration of a dynamically evolving system. Less speculative is the observation that effective physical laws already differ depending on the scale and energy regime we examine. At everyday human scales, classical Newtonian physics adequately describes most phenomena. At high speeds, relativistic effects become important. At small scales, quantum mechanics governs behavior. At high energies, quantum field theory provides the appropriate framework. While the underlying laws remain consistent, their practical manifestations change dramatically across different domains. As the universe ages and cools, transitioning through distinct cosmic eras, the relevant physical domains shift accordingly. The early universe's extreme densities and temperatures made quantum field theory and general relativity the dominant frameworks. Our current stelliferous era involves complex interplay between nuclear, atomic, and gravitational physics. The far future, with its extreme dilution and low temperatures, will be governed primarily by quantum fluctuations, tunneling effects, and information theory. The applicable laws evolve even if the fundamental equations remain fixed. This evolution becomes particularly relevant when considering extreme limits. Physics, as we understand it, breaks down in several crucial scenarios: at the Big Bang singularity, at the center of black holes, at the Planck scale where quantum gravity becomes essential, and potentially at the end state of an infinitely expanded universe. These boundaries mark the limits of our current theories, suggesting deeper principles may underlie what we currently regard as fundamental laws. Quantum gravity, the yet undiscovered framework unifying general relativity with quantum mechanics, likely introduces significant revisions to our understanding of spacetime itself. Various approaches, including string theory, loop quantum gravity, and causal set theory, suggest spacetime might be emergent rather than fundamental, arising from deeper quantum structures. If true, the laws governing spacetime might fundamentally change under sufficiently extreme conditions, such as those in the far future universe. One specific proposal for evolving laws comes from cosmologist Lee Smolin's theory of cosmological natural selection. This framework suggests black holes might create new universes with slightly modified physical laws. Universes that produce many black holes would generate more offspring, naturally selecting for physics conducive to black hole formation. Over many cosmic generations, physical laws would evolve toward configurations that maximize black hole production, potentially explaining our universe's apparent fine-tuning for complexity. Another approach considers the renormalization group in quantum field theory, which describes how physical parameters change with energy scale. As the universe cools over trillions of years, the relevant energy scales shift dramatically, potentially causing corresponding shifts in effective coupling constants and interaction strengths. What appears constant over billions of years might reveal slow evolution over trillions or quadrillions of years as cosmic conditions change. The cosmological constant presents a particularly interesting case for potential evolution. Current observations indicate this value, which determines the universe's accelerated expansion rate, is bizarrely small compared to theoretical expectations, yet non-zero. Some models suggest the cosmological constant might gradually decrease over time, potentially approaching zero in the extremely distant future. Such evolution would dramatically alter cosmic expansion, perhaps eventually halting or even reversing it. This possibility connects to various cyclic universe models, where expansion eventually reverses into contraction, potentially leading to a big bounce and a new cosmic cycle. While current evidence favors eternal expansion, our observational window spans merely 14 billion years of cosmic history. Processes operating over trillions or quadrillions of years might reveal different long-term behavior, including potential cyclicity with different physics emerging in each new cycle. Even without such dramatic transformations, the changing cosmic environment alters which physical processes dominate. The early universe featured primordial nucleosynthesis, where light elements formed from protons and neutrons. Our current era features stellar nucleosynthesis, creating heavier elements in star cores and supernovae. The far future might feature quantum nucleosynthesis, where extremely rare tunneling events occasionally produce new configurations of particles. The underlying nuclear physics remains the same, but its manifestations and relevant timescales change profoundly. Similarly, information processing undergoes evolution across cosmic history. In the early universe, information existed primarily in the distribution of energy and elementary particles. Our current era features complex information structures like DNA, brains, computers, and ecosystems. The far future might preserve information in subtle quantum correlations between extremely distant particles, in the precise radiation patterns of evaporated black holes, or in rare fluctuations from equilibrium. Information persists but transforms across cosmic eras. Particularly intriguing is the evolution of causal structure itself. General relativity teaches us that gravity curves spacetime, altering the paths light rays follow and the ways events influence one another. In the early dense universe, causal connections were limited to relatively nearby regions. As space expands, our current era allows causal connections across billions of light years. The far future features isolated causal patches, regions forever disconnected from one another by accelerating expansion. The network of possible cause and effect relationships evolves dramatically, even if the laws governing causality remain fixed. Time itself might evolve in its manifestation and meaning. In thermodynamic terms, time's arrow points from lower to higher entropy, from order to disorder. This creates asymmetry between past and future that makes time feel directional. But in the far future, as the universe approaches maximum entropy, this directional quality might diminish. With rare events separated by vast durations of effectively nothing, time might lose its flow like character, becoming instead a sparse collection of disconnected happenings with no meaningful sequence. These examples illustrate an important distinction between the fundamental equations of physics and their manifestation in the real universe. Equations like Einstein's field equations for gravity or the Schrödinger equation for quantum systems might remain unchanged, while their solutions, the physical states they describe, evolve dramatically over cosmic time. The laws themselves might be eternal, while the behaviors they generate transform completely. This perspective echoes the distinction between syntax and semantics in language. The grammatical rules may remain fixed, while the meanings expressed through them vary infinitely. Similarly, mathematical physics provides the syntax, the formal structure of the universe, while the actual configurations of matter and energy, the solutions to those equations, provide the semantics, the realized meaning that changes over time. Beyond these relatively conservative possibilities lies more radical speculation. Some theoretical frameworks suggest fundamental physical laws might actually be evolutionary, subject to variation and selection processes, analogous to biological evolution. These approaches, while highly speculative, address the challenging question of why these particular laws, rather than others mathematically possible, govern our universe. Philosopher of science Paul Davies has proposed that the universe might be capable of self-organization not just in its material configurations but in its fundamental rule structure. Just as complex adaptive systems in biology can rewrite their internal rules through evolution, perhaps the cosmos itself adapts its operational principles over sufficiently long timescales. Such meta-evolution would represent a profound extension of current physics, suggesting the universe possesses emergent goal-directed behavior at the highest level. Mathematician Roger Penrose's conformal cyclic cosmology presents another framework for evolving physics. This model proposes that after all matter decays and all black holes evaporate, the resulting empty universe becomes mathematically identical to the very early universe before matter formed. This equivalence potentially allows a smooth transition between cycles, with information from the previous cycle possibly influencing physical parameters in the next, creating an evolutionary trajectory across multiple cosmic eons. Theoretical physicist Julian Barber suggests time itself might be an emergent feature rather than a fundamental aspect of reality. In this view, the universe consists of a vast configuration space of possible states, with the appearance of time flow emerging from relationships between these states. As cosmic conditions change dramatically, the nature of this emergence might also change, effectively altering how time itself operates without changing the underlying timeless mathematical structure. These speculative frameworks share a common theme, challenging the conventional view of physical laws as immutable entities existing somehow outside the universe they govern. Instead, they propose laws as patterns that emerge from deeper principles, patterns that might evolve as the universe itself evolves. Like the rules of a complex game that change as the game progresses, cosmic laws might develop new features, emphases, or expressions over sufficiently long durations. This evolutionary perspective gains support from recent developments in quantum gravity approaches. Loop quantum gravity, for instance, suggests spacetime itself is not continuous, but composed of discrete units at the Planck scale, roughly 10 to the negative 35 meters. The relationships between these fundamental building blocks, rather than existing within spacetime, actually create spacetime through their interactions. As these relationships evolve over cosmic history, the effective laws governing spacetime might also evolve. String theory similarly proposes fundamental entities, tiny vibrating strings, whose various vibrational modes manifest as different particles and forces. The particular pattern of compactified extra dimensions determines which physics emerges in our four-dimensional spacetime. If these compactification patterns can change, either abruptly through vacuum transitions or gradually through dynamical processes, the effective physical laws would change accordingly, even as the underlying string dynamics remain constant. Even more radical is the possibility that mathematics itself, the language in which we express physical laws, represents only an approximation of deeper principles beyond formal description. Mathematician Kurt Gödel demonstrated that any sufficiently complex formal system contains truths unprovable within that system. Perhaps our mathematical physics similarly captures only an incomplete aspect of reality, with the true cosmic principles partially transcending formal expression and evolving in ways our current mathematics cannot fully represent. These possibilities might seem extremely speculative, venturing beyond conventional science into philosophical territory. Yet the history of physics repeatedly demonstrates that concepts once considered philosophical, like atoms, curved spacetime, or quantum uncertainty, eventually become central to scientific understanding. The evolution of physical laws, while currently speculative, might eventually move from philosophy to established science as evidence accumulates and theories develop. Practical investigation of evolving laws faces enormous challenges. Most potential changes would occur over timescales vastly exceeding human civilization or even terrestrial biology. Detecting a drift in the fine structure, constant of 1 part in a billion per billion years, would require precision measurements across cosmological distances, comparing ancient light to current laboratory values while accounting for numerous confounding factors. However, certain approaches offer potential insight despite these difficulties. Observations of extremely distant quasars and galaxies provide snapshots of physics operating billions of years ago. Laboratory precision measurements over decades can place increasingly tight constraints on present-day variation in fundamental constants. Theoretical models connecting early universe conditions to current observations might reveal inconsistencies requiring evolving parameters to resolve. Astronomical measurements already search for spatial variation in physical constants, which would suggest similar temporal variation might occur. Analysis of ancient light from distant sources using atomic fine structure and molecular rotational transitions can reveal whether fundamental constants differed billions of years ago. The Oklo natural nuclear reactor, which operated approximately 2 billion years ago in present-day Gabon, provides evidence about nuclear physics in Earth's past. While these approaches cannot directly probe the far future, they can establish whether physical constants have remained perfectly fixed or shown slight variation over accessible timescales. Even minimal confirmed variation would revolutionize our understanding, demonstrating that what we consider immutable laws actually evolve, albeit extremely slowly. Such evidence would fundamentally alter our conception of physics itself. The implications of evolving physical laws extend beyond theoretical physics into philosophy, theology, and human understanding of our cosmic context. If laws themselves change over time, our current scientific theories represent not timeless truths, but provisional models applicable to our particular cosmic epoch. Future civilizations, should any exist, might develop radically different physics appropriate to their altered reality. This perspective connects to ancient philosophical traditions that view reality as fundamentally dynamic rather than static. Heraclitus's observation that one cannot step in the same river twice captures this insight, that change rather than permanence characterizes existence. Modern physics, with its block universe of fixed spacetime and eternal equations, tilted toward Parmenidean permanence. Evolving laws would swing the pendulum back toward Heraclitean flux, suggesting change penetrates to reality's deepest level. Theologians might find both challenge and inspiration in evolving physics. Traditional conceptions of divine law often parallel the idea of eternal, unchanging physical law. An evolutionary cosmos with developing principles suggests instead a more dynamic understanding of ultimate reality, perhaps one where creativity and emergence play fundamental roles alongside order and consistency. Such frameworks might align more closely with process theology or certain Eastern philosophical traditions than with classical Western theological models. For humanity's conceptual understanding, evolving laws would require significant adjustment. We instinctively seek permanent knowledge, eternal principles that transcend time and circumstance. The scientific revolution itself developed partly from the conviction that beneath nature's apparent chaos lay immutable mathematical harmony. Recognizing even this harmony as provisional and evolving would transform our intellectual relationship with the cosmos, emphasizing our temporal situatedness rather than access to timeless truth. Yet this evolutionary perspective also offers profound connections between physics and biology, between cosmic and terrestrial development. If the universe itself evolves not just in its material configurations but in its fundamental patterns and principles, then the emergence of biological evolution on Earth reflects a deeper cosmic tendency toward adaptive development. Life would represent not an anomaly in an otherwise fixed reality but an expression of the universe's intrinsic evolutionary nature. This connection appears particularly in complex systems science, which identifies common patterns in adaptive, self-organizing systems across widely different scales and contexts. From chemical reaction networks, to embryonic development, to ecosystems, to economies, to cultures, similar principles of emergence, selection, and evolution operate. If physical laws themselves participate in evolutionary processes, this would extend these principles to the largest scale, suggesting a fundamental unity to all developmental processes, from subatomic to cosmic. As we contemplate the far future, the possibility of evolving laws adds another dimension to cosmic transformation. Not only does matter decay, energy disperse, and structure dissolve, but the very rules governing these processes might themselves change. The strange behavior of physics at the end of the universe might reflect not just extreme conditions applied to fixed laws, but the emergence of new principles appropriate to a fundamentally transformed reality. Perhaps most profoundly, evolving laws challenge the distinction between the universe and its governing principles. Rather than laws existing somehow outside or beyond the cosmos they govern, this perspective places them within the cosmic process, as patterns that emerge, develop, and transform as part of reality's unfolding. The universe becomes not an object governed by external rules, but a self-creating, self-organizing entity whose principles develop organically through its own evolution. As we continue our journey through deep time, this possibility of evolving laws reminds us to hold our current understanding provisionally. The physics we have discovered represents not the final truth, but our best current approximation, valid for the cosmic epoch we inhabit, but potentially inadequate for the universe's distant past or far future. With humility and wonder, we recognize our knowledge as embedded within cosmic history rather than standing outside it, evolving as the universe itself evolves across the vast expanse, and experience consists of matter, assemblies of atoms bound together by electromagnetic forces. Our bodies, our planet, distant stars, and faraway galaxies all comprise the same fundamental ingredients: protons, neutrons, and electrons arranged in patterns of extraordinary diversity and complexity. This material foundation has existed since the universe cooled enough for stable atoms to form, roughly 380,000 years after the Big Bang. For billions of years, matter has provided the enduring substrate for cosmic structure and evolution. Yet in the profound depths of cosmic time, even this seemingly permanent foundation faces dissolution. Given sufficient duration, processes currently so slow as to be practically unobservable will transform or eliminate conventional matter. Atoms will break down, protons and neutrons will decay. The fundamental particles themselves will transmute or disperse until the material universe as we know it ceases to exist. This transformation represents perhaps the most dramatic phase transition in cosmic evolution, the end of matter itself. In our everyday experience, matter appears immutable. We observe chemical reactions where molecular bonds break and reform, but the underlying atoms remain unchanged. We witness state changes where solids melt to liquids or vaporize to gases, but the constituent particles persist. Even in nuclear reactions, where atomic nuclei split or fuse, the component protons and neutrons remain intact, merely rearranging into new configurations. This apparent permanence of fundamental particles shapes our intuitive understanding of physical reality, suggesting an eternal material foundation underlying cosmic existence. The decay of matter begins with complex structures, biological organisms, technological artifacts, and other intricate arrangements break down relatively quickly due to entropy's relentless pressure. Metabolic processes, erosion, chemical degradation, and radiation damage dismantle organization at molecular scales. Given mere thousands or millions of years, even the most durable human constructions return to dust. Within billions of years, geological processes reshape planetary surfaces, erasing all trace of prior structures. More stable material configurations persist longer. Mountains may stand for hundreds of millions of years. Planets remain intact for billions of years. The cores of dead stars, white dwarfs, and neutron stars maintain their integrity for trillions. Yet even these relatively stable forms eventually succumb to various decay mechanisms. Stellar remnants cool and crystallize. Planets either fall into their stars are ejected into interstellar space, or are consumed when their stars expand into red giants. Gradual processes like quantum tunneling and gravitational perturbation disrupt even the most robust material structures. The true end of matter involves more fundamental transmutation. Atoms themselves, once thought eternally stable, eventually transform through several possible mechanisms. The most dramatic of these is proton decay, a hypothesized process wherein protons, the positively charged constituents of atomic nuclei, spontaneously convert into lighter particles. This decay, if it occurs, would ultimately render all conventional matter unstable over sufficient timescales. Proton decay is predicted by many grand unified theories, frameworks that attempt to unify the electromagnetic, weak, and strong nuclear forces as different manifestations of a single underlying interaction. These theories suggest that at extremely high energies, such as those present shortly after the Big Bang, the three forces become indistinguishable. As a mathematical consequence of this unification, baryon number, the quantum property that distinguishes protons and neutrons from other particles, need not be perfectly conserved. The theoretical foundation for proton decay emerges from symmetry principles at the heart of particle physics. Just as electromagnetic and weak forces unify at high energies into the electro-weak force, grand unified theories propose that at even higher energies, approximately 10 to the power of 16 billion electron volts, the strong nuclear force joins this unification. At this grand unification scale, new particles called X and Y bosons would mediate transformations between quarks and leptons, the two fundamental families of matter particles that remain distinct in the Standard Model. These X and Y bosons, far too massive to be produced in any current or planned particle accelerator, would enable processes that convert quarks, the constituents of protons and neutrons, into leptons like electrons and neutrinos. Such conversions would violate the conservation of baryon and lepton numbers individually, while preserving their difference. A proton, containing 3 quarks, could transform into a positron and neutral pion, or other combinations of lighter particles, through the fleeting influence of these hypothetical bosons. While the Standard Model of particle physics, our current best understanding of subatomic particles and their interactions, does not predict proton decay, various extensions to this model do. One common decay channel proposed in grand unified theories converts a proton into a positron, the antimatter equivalent of an electron, and a neutral pion, which quickly decays into photons. Other theoretical channels produce different combinations of particles, but all involve converting the proton's mass to lighter entities and radiation. The theoretical lifetime of a proton depends on the specific grand unified theory considered, ranging from approximately 10 to the power of 31 years to 10 to the power of 40 years or even longer. For comparison, the current age of the universe is roughly 10 to the power of 10 years. Even the shortest estimated proton lifetime exceeds the cosmic age by a factor of 10 billion, explaining why we have never observed this decay despite careful experiments. For decades, physicists have searched for evidence of proton decay using massive detectors filled with water or other materials providing numerous protons for observation. These experiments place ever tighter constraints on the proton lifetime, currently establishing a lower bound of approximately 10 to the power of 34 years. This means that if a proton decay occurs, it happens less frequently than once per 10 to the power of 34 years on average for any given proton. The implications of proton decay for the far future are profound. If protons decay with any non-zero probability, no matter how small, then given sufficient time, all protons in the universe will eventually transform. No ordinary matter will remain permanently stable. Every atom, molecule, and material structure will ultimately disintegrate as their constituent protons convert to radiation and lighter particles. This transformation would proceed unevenly across cosmic time. In the relatively near future, perhaps 10 to the power of 36 years from now, the first noticeable effects would appear in large collections of matter. A 1 kilogram object contains approximately 10 to the power of 27 protons. If the proton lifetime is 10 to the power of 36 years, roughly 1 proton in that kilogram would decay each billion years. Initially, these rare decays would have minimal impact on the object's structure or properties. As time advances, however, the cumulative effect becomes increasingly significant. After approximately 1% of the proton lifetime has passed, a detectable fraction of the object's mass would have transformed. By 10% of the lifetime, the material would be noticeably altered. At 50%, half the protons would have decayed, fundamentally compromising all atomic structures. Eventually, after several proton lifetimes, essentially all protons would have converted to radiation and elementary particles, leaving no conventional matter behind. The timeline for this transformation extends far beyond human comprehension. If the proton lifetime is approximately 10 to the power of 36 years, then after about 10 to the power of 37 years, roughly 90% of all protons will have decayed. By 10 to the power of 38 years, 99% will have transformed. Eventually, no protons will remain, and with them, no atomic nuclei or conventional atoms. Even if protons prove perfectly stable, alternative decay mechanisms may still dismantle matter over longer timescales. Quantum tunneling, a phenomenon where particles can traverse energy barriers impossible to cross in classical physics, enables extremely rare but inevitable transformations. Given the effectively infinite time available in cosmic deep future, even processes with infinitesimal probability per year become certainties. This quantum tunneling represents one of the most fascinating aspects of quantum mechanics. In our everyday classical world, objects cannot pass through barriers without sufficient energy to surmount them. A ball rolling toward a hill stops and rolls back if it lacks the energy to reach the top. But at quantum scales, particles behave according to wave functions that extend through space, giving them a non-zero probability of being found on the other side of an energy barrier, even without sufficient energy to classically cross it. The probability of tunneling depends exponentially on the barrier's height and width, making it extremely unlikely for macroscopic objects but potentially significant for subatomic particles over immense timescales. The alpha decay of radioactive nuclei demonstrates this process in action, with alpha particles tunneling through the strong nuclear force barrier to escape the nucleus. Similar tunneling processes could eventually transform even apparently stable configurations of matter, given sufficient time. One such mechanism involves quantum nucleation, where atomic nuclei tunnel into more energetically favorable configurations. Over extraordinary timescales, roughly 10 to the power of 1,500 years, the nuclei in cold, dense objects like white dwarfs would tunnel into iron nuclei, the most stable nuclear configuration. While stable against further nuclear processes, even these iron nuclei might eventually transmute through more exotic quantum effects over even longer durations. Neutrons bound within atomic nuclei appear stable under ordinary conditions, remaining intact indefinitely in most atoms. Free neutrons, however, decay with a half-life of approximately 10 minutes, converting into protons, electrons, and antineutrinos. This relationship between bound and free states illustrates how stability depends crucially on context and environment. As the universe evolves toward increasingly extreme conditions, particles stable today might become unstable in the distant future. The eventual fate of electrons, the negatively charged particles orbiting atomic nuclei, remains uncertain. Unlike protons and neutrons, electrons appear to be fundamental particles without internal structure in the standard model. However, some theoretical extensions suggest electrons might also decay over extraordinarily long timescales, perhaps 10 to the power of 100 years or longer. If electrons do decay, all remaining matter would eventually convert entirely to radiation and truly fundamental particles. Electrons might also annihilate with their antimatter counterparts, positrons, when the two particles meet. This process converts their combined mass into pure energy, usually in the form of gamma-ray photons. In the present universe, matter vastly outweighs antimatter, making such encounters rare. However, various particle creation processes in the far future might gradually restore matter-antimatter balance, leading to increasing annihilation events that further reduce the matter content of the cosmos. The quantum vacuum itself can produce electron-positron pairs through various mechanisms. Strong electric fields can pull these virtual particles from the vacuum, making them real. Intense gravitational fields, such as those near black holes, can similarly create particle pairs. Even the expanding space of the accelerating universe might eventually produce particles through a process analogous to Hawking radiation. These mechanisms ensure some minimal level of particle creation continues, even as existing matter decays. The balance between creation and destruction determines the universe's long-term material composition. If decay processes outpace creation mechanisms, as current understanding suggests, then matter gradually diminishes, eventually becoming extremely rare. If creation and destruction reach equilibrium, a steady state might emerge, with a sparse but stable population of particles persisting through cosmic deep time. The precise outcome depends on detailed aspects of physics not yet fully understood. As matter decays, the universe undergoes a dramatic phase transition. Without stable protons and neutrons, no atoms can form. Without atoms, no chemistry can occur. Without chemistry, no biology as we understand it can exist. The universe transitions from a matter-dominated state to one filled primarily with radiation and elementary particles separated by ever-increasing distances due to cosmic expansion. This transformation evokes a strange symmetry with the universe's early evolution. During the first few minutes after the Big Bang, protons and neutrons formed from the hot quark-gluon plasma that filled space. For approximately 380,000 years, the cosmos existed as a plasma of free nuclei and electrons, too energetic to combine into stable atoms. Only when expansion cooled this plasma sufficiently did neutral atoms form during the epoch of recombination, allowing light to travel freely and setting the stage for structure formation. In the far future, this process effectively reverses. Atoms disintegrate as their constituent protons decay. The tightly bound structures of matter dissolve into free elementary particles and radiation. The cosmos returns to a state somewhat resembling its pre-atomic phase, but with crucial differences. Instead of hot, dense plasma, the far future universe contains extremely cold, diffuse particles separated by vast distances. Instead of moving toward greater structure and complexity, as the early universe did, this late phase evolves toward ever greater simplicity and homogeneity. This transition alters the relevant physics governing cosmic evolution. Nuclear forces, which bind protons and neutrons, become irrelevant without these particles. Electromagnetic forces, while still fundamental, apply differently to free elementary particles than to bound atomic systems. Gravity, always dominant at the largest scales, becomes effectively negligible at the level of individual particles due to their minute masses and vast separations. Quantum effects, particularly vacuum fluctuations and tunneling phenomena, emerge as the primary drivers of what little activity remains. The energy landscape also transforms dramatically. In the current universe, mass represents a substantial energy reservoir, according to Einstein's famous equation relating mass and energy. Stars convert a small fraction of their mass to energy through nuclear fusion, radiating the resulting energy as heat and light. Matter's abundance makes this the dominant energy source in our cosmic epoch. Without stable matter, this energy source vanishes, leaving only the kinetic energy of remaining particles and the mysterious dark energy that drives cosmic acceleration. The universe becomes increasingly dilute as expansion continues while matter decays. The average density, already incredibly low in intergalactic space today, decreases toward effective emptiness. Photons, the particles of light, redshift to longer wavelengths and lower energies as space expands, remaining material particles separate to distances where interactions become vanishingly improbable. The cosmos approaches what physicists call the heat death, a state of maximum entropy and minimal useful energy. Yet even in this extreme state, isolated quantum events occasionally occur. Rarely, particles might encounter one another, briefly interacting before separating again. Vacuum fluctuations continue to produce virtual particle pairs that quickly annihilate. Quantum tunneling enables occasional transitions between different energy states. These events become increasingly separated in both space and time, creating a sparse network of causal connections stretching across the cosmic void. Information, once densely encoded in matter's structure, disperses across these rare interactions and quantum correlations. Like a hologram shattered into countless pieces, each containing a fragment of the original image, information spreads throughout the cosmos, becoming increasingly difficult to reconstruct but never entirely lost. This preservation of information mandated by quantum mechanics, provides a thread of continuity connecting the empty far future to the matter-rich early universe. The dispersal of information raises profound questions about permanence and meaning in a universe where all material structures eventually dissolve. Information about our civilization, our planet, our individual lives, indeed everything that has ever existed, gradually transitions from localized material encodings to diffuse quantum correlations spread across cosmic distances. Nothing is truly erased, according to fundamental physics, but information becomes increasingly inaccessible, fragmented across countless subtle relationships between particles that may never again interact. This information dispersal follows inevitable thermodynamic principles. Low entropy states, where information is densely encoded in ordered structures, naturally evolve toward higher entropy states, where information spreads across more degrees of freedom. A book contains information densely encoded in the arrangement of ink molecules on paper. Burn the book, and that information disperses into the positions and velocities of countless smoke and ash particles, the thermal radiation released, and the atmospheric molecules rearranged by the resulting convection. The information still exists in principle, but becomes practically irretrievable. The dissolution of matter raises profound questions about the nature of physical existence. If everything we consider substantial eventually converts to radiation and elementary particles, what constitutes reality's enduring foundation? The answer may lie not in any particular type of particle or field, but in the underlying mathematical patterns that govern their relationships and transformations. The physical universe becomes less a collection of things and more a network of processes operating within a mathematical framework. This perspective aligns with certain interpretations of quantum field theory, which describes reality in terms of fields permeating all space, with particles representing excitations of these fields. In this view, fields rather than particles constitute the fundamental ontology. As particles decay and transform, the underlying fields remain, their excitation patterns changing, but their existence continuing. Matter's end thus represents not annihilation but reconfiguration of field states. Some theoretical approaches go further, suggesting information itself might prove more fundamental than either particles or fields. The it from bit concept, proposed by physicist John Wheeler, posits that information represents reality's primary substance, with physical objects and properties emerging from informational patterns. If true, the decay of matter would not eliminate reality, but transform how information manifests physically, from matter-based encoding to more subtle quantum correlations. Quantum mechanics enforces certain conservation laws that constrain how matter can decay. Electric charge must be preserved, requiring decay products to carry the same net charge as the original particle. Energy and momentum must be conserved, limiting which decay channels are energetically possible. Angular momentum, or spin, must also balance between initial and final states. These conservation principles ensure that while matter may end, its fundamental attributes persist in different forms. The eventual disappearance of protons, the building blocks of atomic nuclei, represents a transition as significant as the formation of the first atoms. Just as the early universe transformed from a plasma of free nuclei and electrons to a gas of neutral atoms, allowing light to travel freely and structures to form, the far future universe transforms from a matter-based state to a radiation-dominated one. This transition completes a cosmic cycle, returning the universe to a state somewhat resembling its earliest phases, though vastly colder and more dilute. Biology and consciousness, as we understand them, depend crucially on stable matter. Organic chemistry requires atoms forming molecules of consistent properties. Biological information storage, from DNA to neural patterns, relies on durable material substrates. Thought itself, at least in brain-based organisms, emerges from electrochemical processes in physical neurons. The end of matter thus seems to preclude the continuation of life and mind in any familiar form. However, information and computation need not remain forever bound to their current material implementation. Theoretical work on the physics of computation suggests that information processing can occur through many different physical mechanisms, some potentially viable even in a post-matter universe. Quantum fluctuations, interactions between elementary particles, or patterns in radiation fields might support forms of computation vastly different from biological or electronic systems, but sufficient for some analog of consciousness to persist. Physicist Freeman Dyson speculated that intelligent entities might adapt to the universe's changing conditions, gradually transferring their information patterns from matter-based substrates to alternative media as cosmic conditions evolve. This transition would require profound transformation, abandoning physical bodies for increasingly diffuse and abstract implementations. Whether anything recognizable as consciousness could survive such extreme adaptation remains an open question at the intersection of physics, information theory, and philosophy of mind. Returning to more established physics, the end of matter alters how fundamental forces manifest. Electromagnetism, which governs chemical bonding and most everyday phenomena, continues to influence remaining charged particles like electrons and positrons, but no longer creates the diverse material structures we observe today. The strong nuclear force becomes essentially irrelevant without protons and neutrons to bind. The weak nuclear force, responsible for certain types of radioactive decay, finds few particles left to transform. Gravity, the force that shaped cosmic structure by drawing matter together into galaxies, stars, and planets, becomes increasingly insignificant at the level of individual particles. While still governing the universe's large-scale evolution through cosmic expansion, gravity's role in creating complexity dramatically diminishes. The vast distance between remaining particles makes gravitational clumping effectively impossible, preventing the emergence of new structures through conventional means. Yet paradoxically, as ordinary physics becomes less relevant, more exotic phenomena gain prominence. Quantum gravity effects, negligible under ordinary conditions, might become significant in certain contexts of the far future universe. Virtual black holes, microscopic space-time fluctuations predicted by some quantum gravity approaches, could briefly form and evaporate, creating rare but dramatic local events. Such phenomena, operating at the boundary between established science and theoretical speculation, might introduce novel behaviors into the seemingly empty cosmos. These virtual black holes, quantum fluctuations in spacetime itself, would form and evaporate almost instantaneously, their entire existence spanning perhaps 10 to the power of -43 seconds, the characteristic timescale of quantum gravity, known as the Planck time. During their ephemeral existence, they might connect distant regions of space, temporarily altering the universe's causal structure. They could catalyze particle transformations otherwise forbidden by standard physics, introducing additional decay channels for any remaining particles. They might even, according to some speculative theories, serve as nucleation points for transitions between different vacuum states, potentially initiating localized changes to the effective laws of physics. Similarly, quantum fluctuations might occasionally produce complex structures through exceedingly improbable, but not impossible, random assemblies. Given infinite time, even extremely low probability events eventually occur. Particles might momentarily arrange themselves into configurations resembling atoms, molecules, or more complex systems before dispersing again. While vanishingly rare, such Boltzmann fluctuations, named after the physicist who first explored their theoretical possibility, could briefly recreate small islands of complexity in the otherwise featureless void. The probability decreases exponentially with the complexity of the structure, ensuring that large-scale ordered systems remain effectively impossible, but simple patterns might occasionally emerge from quantum randomness. The dissolution of conventional matter does not represent the absolute end of physical existence. Rather, it marks a transition to a fundamentally different state, one governed by different physical processes, operating at vastly extended timescales. The patterns and principles underlying reality persist, even as their material manifestations transform beyond recognition. Matter's end thus constitutes not a conclusion, but a metamorphosis in the cosmic evolutionary journey. This transformation echoes philosophical traditions that distinguish between substance and form, between underlying reality and its manifest appearances. While the material substance we associate with physical existence eventually disappears, the formal patterns and relationships that define reality's deep structure continue. Just as music transcends the particular instruments that produce it, existing as pattern rather than substance, perhaps reality's essence transcends its material implementation. As we contemplate matter's eventual dissolution, we might feel a profound sense of transience. Everything tangible, everything solid and enduring by human standards, faces ultimate transformation. Yet this very impermanence reveals a deeper form of persistence. The patterns that define physical law, the mathematical relationships that govern cosmic evolution, the information preserved across transformations, these endure even as their material expressions change. The end of matter, viewed from sufficient perspective, represents neither creation nor destruction, but transformation, a cosmic phase transition as significant as the formation of the first atoms or the birth of the first stars. It marks not the universe's conclusion, but another stage in its evolution, as it continues its journey through states of being we can barely imagine, governed by the strange behavior of physics, carrying us from past to future in a continuous stream of moments. This intuitive understanding shapes our entire experience of existence. We watch leaves change color in autumn, observe children grow, witness stars burst into supernovae. These changes, these events, these transformations provide the markers by which we measure time's passage. But what happens in the deep cosmic future when changes become vanishingly rare? When the last stars have faded, when matter has decayed, when even black holes have evaporated, does time itself become meaningless? This chapter explores the strange nature of time without change, the paradoxical state toward which our universe evolves in its final era. Our human experience of time feels deeply intuitive, woven into every aspect of our conscious lives. We perceive duration between events. We distinguish past from present, from future. We sense the flow of seconds, minutes, hours, days, and years. This experiential quality of time seems so fundamental, so self-evident, that we rarely question whether time itself might behave differently under extreme conditions, whether the temporal flow we take for granted might represent merely one manifestation of something more complex and malleable. The question of time's nature has puzzled philosophers and physicists for millennia. St. Augustine famously remarked that he knew what time was until someone asked him to explain it. Our subjective experience of time's flow seems self-evident, yet attempts to define time precisely lead to profound conceptual challenges. Is time an independent dimension, existing regardless of its contents? Or is time merely the measure of change, with no independent reality beyond the transformations it tracks? This question's ancient origins demonstrate its fundamental character. The Greek philosopher Parmenides, writing in the 5th century BCE, argued for a timeless universe where change represents mere appearance rather than fundamental reality. His student Zeno developed famous paradoxes, attempting to show that motion, and hence time, contains logical contradictions and therefore cannot truly exist. Heraclitus, by contrast, emphasized constant flux, famously stating that one cannot step in the same river twice because both the river and the person have changed between steps. This tension between timeless permanence and constant change has persisted throughout intellectual history. Even in everyday language, we reveal our ambivalence about time's nature. We speak of time passing, flowing, or flying, suggesting an entity moving independently of events. Yet we also refer to having no time or making time, implying time depends on our activities and perceptions. We measure time by change, whether the swing of a pendulum, the oscillation of a cesium atom, or Earth's revolution around the sun. Yet we also imagine time continuing, even if every clock stopped, every planet ceased orbiting, every atom froze in place. This latter view, sometimes called relationism, traces back to Aristotle and was developed by philosophers like Gottfried Leibniz, who argued that time represents nothing more than the order of successive events. In this framework, time requires change to have meaning. Without events to sequence, without transformations to order, time itself dissolves as a meaningful concept. The statement, "time passes," becomes empty when nothing happens during that supposed passage. The alternative perspective, absolutism, championed by Isaac Newton, treats time as an independent entity flowing uniformly, regardless of what occurs within it. Like a container that exists whether filled or empty, Newtonian absolute time continues its steady progression, even in the absence of change. This view aligns more closely with our intuitive sense of time as an inexorable current, an independent dimension along which reality extends. Einstein's relativity theories transformed this philosophical debate by demonstrating that time, rather than being absolute, depends on the observer's reference frame. Time dilates at high velocities. It stretches near massive objects. The separation between past and future, between before and after, which seems fixed and universal in our everyday experience, becomes relative to the observer's state of motion and gravitational potential. These discoveries reveal time as more flexible, more contingent than previously imagined. Yet even relativity assumes that events occur, that changes happen, that reality transforms from one state to another. Time in relativity theory remains intimately connected to causality, to the potential for one event to influence another. What happens when this potential dwindles to effectively nothing? How does time behave when the interval between events stretches toward infinity? The universe's far future presents precisely this scenario. As the cosmos expands and cools, as matter decays and energy disperses, events become increasingly rare. To understand what this implies for time itself, we must explore how time connects to thermodynamics, to quantum mechanics, and to information theory, frameworks that illuminate time's behavior under extreme conditions. Thermodynamics provides perhaps the clearest connection between time and change through the concept of entropy. The second law of thermodynamics states that in closed systems, entropy, a measure of disorder or randomness, tends to increase. This creates an arrow of time pointing from lower to higher entropy, from order to disorder, from past to future. We remember the past, but not the future. Eggs break but don't spontaneously reassemble. Heat flows from hot objects to cold ones, never the reverse. These asymmetries define time's direction in our experience. Austrian physicist Ludwig Boltzmann formalized this connection in the 19th century through statistical mechanics. He recognized that high-entropy states are vastly more numerous than low-entropy states. A broken egg can arrange its molecules in countless ways, while an intact egg requires precise molecular organization. The overwhelming statistical tendency toward more probable states creates the arrow of time we experience. Remarkably, this direction emerges from time-symmetric underlying physics. Newton's laws, Maxwell's equations, even Schrödinger's wave equation work identically forward or backward. Only the statistical behavior of complex systems introduces the asymmetry we experience as time's flow. The universe itself represents such a system, evolving from the extraordinarily improbable low-entropy conditions of the Big Bang toward higher entropy states. This cosmic evolution creates the master arrow of time to which all other temporal asymmetries align, the psychological arrow, allowing us to remember past but not future, the causal arrow, with causes preceding effects, the radiative arrow, with waves propagating outward from sources rather than converging inward, the evolutionary arrow, with complexity increasing over geological timescales. All these directional processes derive ultimately from the universe's evolution, from low to high entropy. Yet this entropic arrow does not flow at constant rate throughout cosmic history. Different eras exhibit different rates of entropy increase, different temporal characteristics. The early universe, dominated by rapid expansion and radiation, processed entropy quickly through thermalization of energy. Our current stelliferous era, with its complex structures and energy gradients, generates entropy through countless processes, from stellar fusion to biological metabolism. The far future, with its decayed matter and dispersed energy, will produce entropy at ever-decreasing rates as available energy gradients diminish towards zero. As the universe approaches maximum entropy, this thermodynamic arrow of time weakens. When all energy gradients have dissipated, when all matter has decayed, when all structures have dissolved, entropy effectively plateaus. Further increase becomes negligible. Without substantial entropy change, the thermodynamic distinction between past and future diminishes. Time's arrow loses its directional force when disorder can increase no further. However, maximum entropy does not mean complete uniformity or absolute stasis. Quantum mechanics ensures that fluctuations always occur, that perfect equilibrium remains unattainable. In an extremely high entropy universe, these fluctuations become vanishingly small and rare. but never disappear entirely. Quantum uncertainty, encoded in Heisenberg's famous principle, guarantees some minimal level of change continues even in a universe approaching heat death. These quantum fluctuations provide extremely sparse temporal markers in the far future cosmos. A virtual particle pair might spontaneously appear and disappear. Occasionally, widely separated particles might interact through some vanishingly improbable encounter. A quantum tunneling event might transform one configuration into another. Each such event creates a brief, localized change against the backdrop of near-perfect stasis. These isolated incidents, separated by incomprehensibly vast durations, represent the last remaining instances of what we might call happenings or occurrences. The mathematics of quantum fluctuations reveals their extraordinary rarity in the far future. Consider a simple quantum event, like the spontaneous appearance of a virtual electron-positron pair. The probability of such an event occurring in a given volume of space during a specific time interval depends inversely on the universe's size and temperature. As cosmic expansion continues and temperature approaches absolute zero, this probability plummets exponentially. A fluctuation that might occur billions of times per second in today's universe might happen just once per trillion years in the far future state. Moreover, these fluctuations become increasingly isolated both spatially and causally. In our present universe, quantum events can trigger causal chains affecting macroscopic systems. A single photon can trigger a chemical reaction, potentially initiating complex processes with widespread effects. In the far future, with its extreme dilution and minimal energy gradients, each quantum fluctuation likely remains causally isolated, unable to trigger broader changes or communicate information across significant distances. The light cone of each event, the space-time region it can causally influence, contains virtually nothing capable of registering or responding to that influence. This causal isolation creates what physicist Seth Lloyd calls causal islands, regions whose events cannot affect one another due to spatial separation and cosmic expansion. As the universe continues expanding, these islands shrink until eventually each elementary particle effectively constitutes its own isolated universe, unable to significantly interact with or influence anything else. Time within each island continues in the minimal sense of quantum state evolution, but the synchronization or coordination of time across different islands becomes increasingly meaningless. The intervals between these rare events extend far beyond human comprehension. Currently, changes occur constantly at all scales, from subatomic oscillations measured in fractions of a second to geological processes spanning millions of years. In the far future, quintillions of years might pass between significant quantum events in any given region of space. The cosmic calendar becomes almost entirely empty, with meaningful change reduced to isolated points separated by near eternity. This sparseness raises profound questions about time's nature. If events become vanishingly infrequent, what fills the supposedly temporal gaps between them? Can we meaningfully speak of time passage when nothing happens during that passage? The absolutist would maintain that time continues its flow regardless, an empty container waiting to be filled. The relationist would counter that these gaps represent not time passing but time's absence, regions where the concept of temporal duration loses, meaning due to change's absence. The philosopher Sidney Shoemaker proposed a thought experiment to address this question. Imagine a universe divided into 3 regions, A, B, and C. Periodically, each region freezes for 1 year, during which all processes there halt completely. Region A freezes every 3rd year, Region B every 4th year, and Region C every 5th year. The overlapping freeze patterns ensure that at least one region always remains active, allowing inhabitants to detect and measure the freezes in other regions. Now imagine all 3 regions simultaneously freezing. Would time pass during this universal pause? Would the duration exist despite nothing experiencing or measuring it? This thought experiment highlights the difficulty of conceptualizing time without change. Our usual methods for measuring time, whether heartbeats, pendulum swings, atomic oscillations, or planetary orbits, all rely on regular, repeated changes. Without such changes, how could any clock mark time's passage? And without the possibility of measurement, what empirical meaning could we assign to the claim that time continues flowing? In the far future universe, change becomes not fully absent but extraordinarily dilute. The resulting timescale mismatch creates perceptual challenges. Consider how differently time appears to various organisms, even on present-day Earth. A mayfly experiences its day-long life as we might experience decades. Geological processes that seem glacially slow to human perception would appear as rapid transformations if viewed at appropriate timescales. The far future's temporal structure similarly depends on the reference framework, with its sparse events appearing either as isolated incidents in a nearly changeless void or as a continuous progression when viewed at appropriately expanded scales. This temporal perspective challenge connects to the concept of time as emergent rather than fundamental. Various approaches to quantum gravity, the yet undiscovered framework unifying general relativity with quantum mechanics, suggest space-time itself might emerge from deeper quantum structures. Time as we experience it would represent not a basic feature of reality, but a large-scale approximation, similar to how temperature emerges from molecular motion rather than existing at the level of individual particles. The analogy with temperature proves particularly illuminating. We experience temperature as a simple, continuous property, the quality of hotness or coldness. Yet physicists understand temperature as the average kinetic energy of particles in a system. A single isolated particle cannot meaningfully have a temperature. The concept requires a statistical ensemble. Similarly, time as we experience it might require an ensemble of interactions, events, and causal relationships. When these become sufficiently sparse, as in the far future universe, conventional time might dissolve, not because some cosmic clock stops ticking, but because the underlying ensemble no longer supports the emergent property we call time. This emergence perspective appears in various theoretical approaches. In loop quantum gravity, space-time emerges from a network of relationships called spin networks, quantum entities that exist in a fundamentally timeless context. Their relationships create what we experience as space-time geometry, including temporal dimension. As these relationships evolve toward the far future configuration, with minimal interaction and maximal separation, the emergent temporal property would transform accordingly, becoming increasingly tenuous and discontinuous. If time emerges from more fundamental relationships, its behavior might change dramatically when the underlying conditions shift sufficiently. In the high-energy early universe, during inflation and the quark epoch, time might have manifested differently than in our current era. Similarly, in the far future's extremely low-energy state, with its near absence of interactions and events, time's emergent properties might transform once again, revealing different aspects of its underlying nature. One framework for understanding time's potential emergence comes from information theory. Physicist Carlo Rovelli has proposed that time represents the manifestation of correlations between physical systems, the network of cause and effect relationships that connect different configurations of reality. In this perspective, time does not flow externally to physical processes, but emerges from the information shared between systems as they interact and evolve. Rovelli's relational quantum mechanics extends this insight into what he calls thermal time, where time emerges from the statistical behavior of complex systems, rather than existing as an independent parameter. When a system reaches equilibrium, its internal temporal structure essentially vanishes, with all microstates becoming equally probable. In the far future universe approaching thermal equilibrium, conventional time would dissolve not because some external time dimension ceases, but because the internal correlations that generate temporal structure diminish toward insignificance. This information-theoretic approach connects to the concept of algorithmic complexity. Systems with high algorithmic complexity require extensive information to describe completely. Their evolution follows patterns too complex for simple representation, creating what we experience as temporal depth or history. As the universe approaches equilibrium, its algorithmic complexity decreases. Fewer bits of information become necessary to specify its state completely. This information-theoretic simplification corresponds to the thinning of temporal structure, the universe becoming increasingly characterized by a single state rather than a complex historical trajectory. Further extending this perspective, theoretical computer scientist Scott Aaronson has explored connections between computational complexity and fundamental physics. He suggests that the arrow of time might relate to the asymmetry between computation and decomputation, between calculating an answer and verifying one already calculated. Many problems require extensive computational resources to solve, but minimal resources to verify. This computational asymmetry potentially underlies temporal asymmetry, with the universe computing its future state from present conditions through a process requiring extensive resources, creating what we experience as time's forward flow. This informational view of time carries profound implications for the far future. As interactions become increasingly rare, as information processing slows to near cessation, time in the conventional sense grows thin. The information theoretic threads, connecting one state to another, stretch to breaking point, creating a cosmos where conventional temporal relationships barely apply. Time does not disappear entirely, but transforms into something sparse, discontinuous, fundamentally different from our ordinary experience. Quantum mechanics introduces additional complications through entanglement, the phenomenon Einstein called spooky action at a distance. Particles that interact become entangled, their properties correlated, regardless of the separation between them. This non-local connection persists, even as the universe expands, creating an intricate web of quantum relationships spanning the cosmos. These correlations preserve information about past interactions, potentially providing a quantum memory that transcends conventional temporal limitations. The mathematics of quantum entanglement reveals its extraordinary resilience. Once established, entanglement persists regardless of spatial separation, creating what physicists call EPR correlations after Einstein, Podolsky, and Rosen, who first explored the phenomenon. These correlations connect particles that might never again interact directly, preserving their relationship across cosmic distances and durations. As particles disperse throughout the expanding universe, they carry with them this web of quantum connections, a gossamer network of correlations stretching across the void. This entanglement network could preserve temporal information long after conventional structures have dissolved. When particles interact, they generally become entangled, encoding information about that interaction in their correlated quantum states. This information remains accessible in principle, though increasingly difficult to access in practice as the particles separate. The universe thus accumulates a quantum memory, with each interaction leaving its trace in the entanglement patterns that span the cosmos. This memory preserves a form of history, even as conventional temporal markers fade. Some theoretical approaches even suggest space-time itself emerges from quantum entanglement. Mark van Ramsdonk and others have explored how entanglement between quantum systems might generate the space-time fabric described by general relativity. In this perspective, entanglement creates not just correlations within space-time, but the very space-time within which those correlations exist. The geometry of space and the flow of time emerge from the entanglement structure of more fundamental quantum entities. As this entanglement structure evolves toward the far future configuration, space-time itself would transform accordingly, potentially creating the strange temporal properties we are exploring. In the far future, with its extreme spatial separation between particles, these quantum correlations might represent the primary repository of whatever temporal structure remains. The universe would exist not as a sequence of events in conventional time, but as a vast network of entangled quantum states, preserving relationships established during earlier cosmic epochs. Time would manifest not through local changes, but through the non-local structure of this quantum network. The physicist Julian Barbour has developed this perspective into what he calls timeless physics. In this framework, now moments, complete configurations of the universe, exist as points in a vast abstract space of possibilities called configuration space. What we perceive as time's flow represents not an external dimension, but the particular path connecting different configurations. Causality emerges from the structure of this path, rather than from time as an independent entity. In his book, The End of Time, Barbour explores this timeless perspective through what he calls the Platonia, the complete collection of all possible now moments, or complete configurations of the universe. Within this Platonia, certain configurations connect to others through relationships resembling what we call causality. These connections create paths of related configurations, which we experience sequentially and interpret as temporal flow. But the Platonia itself has no time dimension. It contains all possible configurations simultaneously in a timeless context. From this perspective, the universe never moves through time. Instead, different configurations exist tenselessly, with certain configurations containing records or memories that create the impression of past events. Our sense of time's flow emerges from these record structures rather than from any external temporal dimension. When we remember yesterday, we're not reaching back through time, but accessing memory structures within our current configuration that correlate with what we call yesterday's configuration. Applied to the far future universe, this timeless framework suggests intriguing possibilities. As change diminishes, as events become increasingly sparse, the path through configuration space approaches a nearly static trajectory, hovering around a particular configuration with only quantum variations. The record structures that create the appearance of temporal flow become minimal. The universe does not freeze at a moment in time, but approaches a configuration with minimal internal temporal structure, minimal capacity to generate the appearance of time's passage. Applied to the far future, this perspective suggests the universe increasingly resembles a single static configuration rather than a dynamically evolving system. With minimal change occurring, the configuration space path becomes nearly stationary, hovering around a particular state with only minute quantum variations. Time does not cease entirely but slows to near imperceptibility as the cosmos approaches its final configuration. The theoretical physicist Sean Carroll extends this analysis through his concept of the Carroll boundary, a hypothetical final state toward which our universe evolves. This boundary represents not a moment in time, but the asymptotic limit of cosmic evolution, a state of near-perfect thermal equilibrium approached, but never quite reached due to quantum fluctuations. The Carroll boundary exists not in temporal terms, but as the basin of attraction toward which all physical processes ultimately converge. As the universe approaches this boundary, conventional time diminishes in relevance. The cosmos transitions from a dynamically evolving system to an effectively static configuration occasionally disturbed by quantum fluctuations. These disturbances, rather than marking time in the ordinary sense, represent deviations from equilibrium that themselves have no inherent temporal order when viewed at the largest scales. The universe does not move through time toward this state. Rather, time dissolves as the state emerges. This dissolution of conventional time connects to the philosophical concept of eternal return or eternal recurrence, most famously articulated by Friedrich Nietzsche. In a universe that exists forever with finite possible configurations, any particular state will eventually recur, given sufficient duration. Applied to quantum fluctuations in the far future, this suggests that any configuration produced by random variations must eventually repeat, creating cycles of recurrence, spanning timescales beyond comprehension. However, our universe's accelerating expansion complicates this picture. As space stretches, the possible configurations increase rather than remaining finite. Particles separate beyond their mutual event horizons, effectively creating multiple isolated systems that cannot interact. This fragmentation potentially prevents true recurrence, as each isolated region evolves independently, unable to coordinate with others to recreate previous global states. The relationship between time and consciousness introduces yet another dimension to this exploration. Our subjective experience of time, the felt passage of moments, emerges from neural processes operating at particular speeds and scales. In the far future, if consciousness could somehow persist in radically different substrates, temporal experience might transform accordingly. A mind operating through extremely rare quantum fluctuations might experience subjective temporality, utterly unlike human perception, perhaps integrating across vast objective durations to maintain continuity of experience. Philosopher David Chalmers, in discussing what he calls the hard problem of consciousness, highlights the mysterious connection between physical processes and subjective experience. This connection becomes particularly puzzling when considering temporal awareness. Why do we experience time's flow at all? Why does consciousness unfold as a sequence of moments rather than existing tenselessly, all at once? These questions gain new significance when contemplating consciousness at the end of time, when conventional sequential processes become vanishingly rare. Neuroscience provides some insight into our temporal perception through studies of time consciousness. Our brains construct the experience of temporal flow through multiple mechanisms operating at different timescales. The specious present, our sense of nowness, spans approximately a few hundred milliseconds, during which our brains integrate information into a unified conscious moment. Working memory extends this temporal window to seconds or minutes. Episodic memory creates our sense of autobiographical continuity across longer durations. Each of these mechanisms depends on specific neural processes operating at characteristic rates. In the far future universe, with its sparse events and minimal energy gradients, these characteristic timescales would necessarily change dramatically. Any form of consciousness persisting under such conditions would require radically different temporal integration mechanisms. Perhaps consciousness could operate through quantum coherence, maintained across vast durations, integrating rare fluctuation events into a continuity of experience utterly unlike our sequential awareness. Or perhaps consciousness might manifest as momentary flashes of awareness, brief islands of experience, separated by effective eternities of non-consciousness. Physicist Freeman Dyson speculated about such possibilities in his paper, Time Without End, suggesting intelligence might adapt to the universe's changing conditions by operating increasingly slowly as energy becomes scarce. As available energy decreases exponentially, conscious processing would slow proportionally, allowing subjective experience to continue indefinitely despite objective time stretching toward infinity. In this scenario, an infinite subjective future could fit within the physical constraints of cosmic evolution. This adaptive slowing connects to relativistic time dilation, just as time slows for objects approaching light speed or experiencing strong gravitational fields. A form of cosmic time dilation might occur for appropriately structured information processing systems as the universe approaches equilibrium. Objective durations would stretch ever longer between significant events, but subjective experience might maintain its continuity by adjusting its timescale to match available energy and complexity. The concept of subjective time without objective change appears in various theological and philosophical traditions. The eternal now, described by mystics, represents a state of consciousness transcending ordinary temporal succession. Plotinus wrote of the one existing in an eternal present, neither becoming nor changing, yet somehow encompassing all possibilities. Various contemplative practices across cultures aim to glimpse this timeless awareness, suggesting subjective temporal experience might decouple from external change under appropriate conditions. Physics offers its own version of the eternal present through block universe theory, which emerges naturally from special relativity. In this framework, past, present, and future exist simultaneously as different regions of a four-dimensional space-time block. Our sense of now, of the present moment, represents not an objective feature of reality, but a subjective perspective within this unchanging whole. Time does not flow. Rather, we move through the block, experiencing different slices as the present. Einstein himself expressed this perspective after developing relativity theory. In a letter to the family of his deceased friend Michel Besso, Einstein wrote, "Now he has departed from this strange world a little ahead of me. That means nothing. People like us, who believe in physics, know that the distinction between past, present, and future is only a stubbornly persistent illusion." This statement captures the profound reconceptualization of time inherent in relativistic physics, where temporal relations depend on reference frame and all moments exist tenselessly within the four-dimensional manifold of space-time. Special relativity demolishes the concept of absolute simultaneity, showing that observers in different reference frames disagree about which events occur simultaneously. This relativity of simultaneity makes it impossible to define a universal now that all observers would agree upon. What appears as a single present moment to one observer contains events that lie in another observer's past or future. This observer dependence suggests the flow of time represents a perspective rather than an absolute feature of reality, supporting the block universe interpretation. General relativity extends this insight by showing how gravity curves spacetime, creating even more complex temporal relationships. Near massive objects, clocks run slower due to gravitational time dilation. Different regions of space can have dramatically different temporal properties. Black holes warp spacetime so severely that inside their event horizons, spatial and temporal dimensions effectively switch roles. These relativistic effects reveal time as dynamic and malleable rather than absolute and fixed, further supporting the block universe perspective where all moments exist equally rather than coming into and out of existence sequentially. Applied to the far future, the block universe perspective suggests that time without change represents not the universe freezing at a particular moment, but our reference frame stretching across increasingly vast space-time segments due to the absence of distinguishing features. Without events to separate one moment from another, the boundaries between past, present, and future blur, approaching the timeless perspective inherent in the block universe model. This blurring connects to the concept of symmetry breaking in physics. Many physical systems exhibit particular behaviors because some fundamental symmetry has been broken, creating distinguishable directions or states where multiple options would otherwise be equivalent. Time's apparent flow from past to future represents such a broken symmetry, established by the universe's initial low entropy condition. As entropy approaches its maximum in the far future, this broken symmetry begins to heal, restoring the time reversal symmetry inherent in fundamental physics. Most equations in basic physics work equally well forward or backward in time. Newton's laws, Maxwell's equations, even Schrödinger's wave equation remain invariant under time reversal. Only the second law of thermodynamics introduces a clear temporal asymmetry. As entropy plateaus, this exception diminishes in relevance, allowing the underlying time-symmetric nature of physics to re-emerge. Time without change thus represents not an aberration, but a return to the fundamental time symmetry disguised by our current cosmic epoch. This symmetry restoration creates philosophical paradoxes. If fundamental physics has no intrinsic time direction, why does our universe display such clear temporal asymmetry? Physicist Roger Penrose's conformal cyclic cosmology addresses this question by proposing that the far future state, with its diffuse radiation and elementary particles, becomes mathematically identical to the very early universe. This equivalence potentially allows a smooth transition between cycles, with the heat death of one universe becoming the Big Bang of another, creating an eternal sequence of cosmic epochs. Penrose's model builds on the mathematical similarity between two seemingly different states: the infinitely expanded, maximally entropic far future universe and the infinitely compressed, minimal entropy early universe. Both states consist primarily of massless particles moving along light-like paths. By applying a conformal transformation, essentially a rescaling that preserves angles while changing distances, one can mathematically map the end state of one cosmic cycle onto the beginning of another. The entropy generated throughout one cycle becomes hidden during the transition, allowing the next cycle to begin in an apparently low entropy state. This cyclical model provides one potential resolution to the puzzle of time's arrow. Rather than representing a one-way journey from order to disorder, cosmic evolution might form an endless cycle, with the apparent temporal direction in each cycle merely a local phenomenon within a greater timeless pattern. The second law of thermodynamics would remain valid within each cycle, while the universe as a whole maintains a kind of eternal recurrence, never reaching a final state of absolute equilibrium. Other theories suggest our universe represents just one bubble in a vast multiverse, with new universes continuously forming through quantum fluctuations in the false vacuum. In this scenario, our cosmic time might end, while time in the broader multiverse continues through the birth and evolution of other universes with their own temporal structures. Time would end locally while persisting globally, creating a nested hierarchy of temporal domains. These speculative frameworks highlight how profoundly time's nature might change as the universe approaches its final state. The conventional flow from moment to moment gives way to something more tenuous, more fragmentary, more disconnected. Events become islands in an ocean of near stasis. Causality stretches to breaking point as effects separate from causes by durations approaching infinity. The temporal fabric thins until only quantum threads remain, connecting rare fluctuations across the void. Yet remarkably, even in this extreme state, time does not disappear entirely. It transforms, dilutes, evolves into something barely recognizable, but not completely absent. Quantum indeterminism ensures some minimal level of change continues indefinitely. Information, though dispersed and diffuse, persists in subtle correlations that span the cosmos. The universe never reaches absolute equilibrium, absolute uniformity, or absolute stasis due to these quantum effects. Time without change thus represents not time's absence but its ultimate manifestation, stripped of the contingent features that dominate our current experience. Like a frozen river revealing structure normally hidden by flowing water, the near motionless cosmos of the far future reveals time's fundamental nature more clearly than the dynamic processes of our present era. When change becomes vanishingly rare, what remains of time shows its essential character, its irreducible features distinct from the events it usually contains. This final temporal state echoes philosophical traditions distinguishing between chronos, sequential time marked by events, and kairos, time's fullness or significance beyond mere succession. As chronos thins toward disappearance, perhaps something like kairos remains, a temporal quality, not dependent on counting moments, but on the holistic integration of all possible configurations. The universe approaches not timelessness but time's essence, purified of the changes that normally obscure its fundamental nature. The strange behavior of time without change thus represents not cosmic death, but cosmic transformation, not an ending, but an evolution toward a state largely beyond our conceptual framework. Our language, evolved to describe changes occurring at human scales, struggles to capture this condition. Our mathematics points toward it through equations, but cannot fully express its experiential quality. Our philosophy circles it through reason, but never completely encompasses its paradoxical nature. As we contemplate this ultimate temporal state, we encounter not just the limits of physics, but the boundaries of thought itself. Time without change challenges our most basic assumptions about reality, about existence, about meaning. Yet this challenge does not signal failure, but opportunity, inviting us to expand our understanding beyond conventional categories, to glimpse, however dimly, the strange fate toward which our universe evolves across the vast expanse. That mysterious inner light through which we experience existence seems inextricably bound to the warm complexity of living brains. Our thoughts, feelings, perceptions, and awareness emerge from intricate networks of neurons, exchanging electrochemical signals, powered by the metabolism of living cells, supported by bodies that extract energy from environments rich in thermodynamic gradients. This biological foundation appears essential to consciousness as we know it, rooted in the specific conditions of our cosmic moment. But what might become of consciousness, or something resembling it, in the deep future universe? Could awareness persist when stars have burned out, when conventional matter has decayed, when time itself has thinned to near meaninglessness? This speculative frontier beckons us to explore the ultimate fate of mind at the end of cosmic time. Our exploration begins with the seemingly outlandish question, could consciousness exist in a universe approaching heat death? Most immediate responses trend negative. After all, our brains require substantial energy flow, approximately 20 watts of continuous power, to maintain conscious awareness. They depend on precise electrochemical balances, specific molecular structures, and elaborate cellular architectures that evolved over billions of years in particular environmental conditions. When the universe consists primarily of diffuse elementary particles separated by vast distances, with minimal energy gradients and near maximum entropy, how could anything remotely resembling consciousness persist? Yet this question contains hidden depth, touching on fundamental issues in the philosophy of mind, information theory, quantum physics, and cosmology. To address it meaningfully, we must first examine what consciousness essentially is, what minimal physical conditions might support it, and how it might adapt to radically different cosmic environments. This inquiry carries us beyond established science into speculative territory, yet remains grounded in physical principles and philosophical reasoning, rather than mere fantasy. Various philosophical frameworks offer different perspectives on consciousness and its relationship to physical reality. Functionalism suggests consciousness emerges from the functional organization of a system rather than its specific physical substrate. In this view, consciousness requires particular informational patterns and processing relationships, potentially implementable in diverse physical media. Biological brains represent just one possible consciousness-supporting substrate among many theoretical alternatives. Panpsychism takes a more radical approach, proposing that consciousness or proto-consciousness exists as a fundamental feature of reality, present in some form at all levels from elementary particles upward. In this framework, our complex human awareness represents an integrated combination of more basic conscious elements present throughout nature. Rather than consciousness emerging at some threshold of complexity, it exists everywhere in simpler forms, becoming more elaborate and self-reflective in complex systems like brains. Information theories of consciousness, like Giulio Tononi's integrated information theory, suggest consciousness emerges when information integrates in specific ways, creating complexes with causal power greater than the sum of their parts. These approaches quantify consciousness through measures like phi, which captures a system's integrated information. Higher phi values correspond to richer conscious experiences. Such theories potentially allow consciousness to exist in any system with sufficient informational integration, regardless of its physical composition. Quantum theories of consciousness, including Roger Penrose and Stuart Hameroff's orchestrated objective reduction model, propose that consciousness relates to quantum processes operating in brain structures like microtubules. These approaches suggest consciousness involves quantum coherence, entanglement, or other non-classical phenomena, rather than emerging solely from classical computation. If correct, such theories might open possibilities for consciousness in quantum systems, quite unlike biological brains. These diverse frameworks offer different pathways for considering consciousness in the far future universe. If consciousness requires only the right functional organization, perhaps it could exist in novel substrates adapted to low energy conditions. If consciousness represents a fundamental feature of reality, perhaps it persists in some form even as complex structures dissolve. If consciousness emerges from integrated information, perhaps sparse but extensive quantum correlations might support minimal awareness. If consciousness involves quantum processes, perhaps quantum fluctuations in the vacuum might maintain some form of proto-consciousness indefinitely. Before exploring these speculative possibilities, we should consider consciousness from an energy perspective. Our brains consume substantial energy, roughly 20% of our body's total, despite constituting only 2% of body weight. This energy powers information processing through action potentials, neurotransmitter release, protein synthesis, membrane maintenance, and countless other mechanisms. Consciousness appears energetically expensive, requiring significant thermodynamic gradients to sustain its operations. The physicist Freeman Dyson pioneered analysis of consciousness under conditions of declining available energy in his paper, Time Without End, published in 1979. Dyson considered whether consciousness might adapt to an ever-cooling universe by processing information more slowly as energy becomes scarce. In principle, a consciousness could maintain subjective richness by extending computation over longer physical durations, sacrificing speed to preserve complexity as available energy decreases. This approach suggests a trade-off between energy consumption, processing speed, and consciousness quality. With fixed energy, a system can compute quickly for a short time or slowly for a long time. As cosmic energy sources dwindle, consciousness might slow asymptotically, stretching each subjective moment across increasingly vast objective durations. From an external perspective, such a consciousness would appear increasingly static. From its internal perspective, subjective experience might continue indefinitely, though with ever-increasing pauses between computational steps. Dyson considered how life and thought might adapt to various cosmic futures, given different scenarios for universal expansion and energy availability. He demonstrated mathematically that even with steadily decreasing temperature and energy density, an appropriately designed system could perform unlimited subjective thinking, given unlimited time. The key insight involved adjusting metabolic and computational rates to match available energy, allowing information processing to continue indefinitely despite diminishing resources. This analysis assumed relatively conventional physics, with matter and energy maintaining their familiar properties. But as we've explored in previous chapters, the far future universe involves more exotic conditions. Protons may decay, black holes eventually evaporate, space continues expanding, separating particles beyond causal contact. Quantum fluctuations become the primary source of novelty and change. How might consciousness fare under these more extreme circumstances? The theoretical computer scientist Jürgen Schmidhuber has extended this analysis through algorithmic information theory. He proposes consciousness as a compression algorithm, a process that identifies patterns in sensory data to predict future inputs. Consciousness continuously creates and updates an internal model of reality, using that model to minimize surprise. This computational perspective suggests consciousness requires only the ability to process and compress information, potentially achievable through diverse physical implementations. Under far future conditions, such compression-based consciousness might operate through extremely rare interactions between widely separated particles. Each interaction creates information, a deviation from expected behavior given previous interactions. A sufficiently extensive network of such interactions could theoretically support a form of distributed consciousness, operating at timescales incomprehensibly slow by human standards, but potentially rich in subjective experience relative to its own temporal frame. This possibility connects to integrated information theory's suggestion that consciousness emerges when information integrates to create a whole greater than the sum of its parts. In the far future, quantum entanglement might preserve integration across vast distances, maintaining causal relationships between particles despite their separation. The resulting integrated information complex, though sparse and slow compared to brains, might support a form of consciousness adapted to cosmic deep time. These speculative frameworks highlight a recurring theme in our exploration. Consciousness may be substrate independent, capable of existing in radically different physical implementations provided certain functional or informational criteria are met. The specific biochemical structures of brains may represent just one possible consciousness supporting architecture among many alternatives, some potentially viable under far future conditions, invisible to biological evolution. To explore these alternatives, consider consciousness in progressively more extreme cosmic futures. As stars exhaust their fuel over the next 100 trillion years, planets cool, and complex chemistry becomes energetically unfavorable, conventional biological consciousness will certainly end. But consciousness might adapt by transferring to more durable substrates, perhaps beginning with technological implementations and transitioning through increasingly exotic physical media as cosmic conditions evolve. One proposal for consciousness in the post-biological era comes from artificial intelligence researcher Hans Moravec, who suggested transferring human minds to computational substrates through detailed scanning and simulation of neural structures. Such substrate-independent minds might operate initially in computers similar to current technology, then migrate to increasingly durable and energy-efficient platforms as environmental conditions deteriorate. Each transition would preserve continuity of consciousness while adapting its physical implementation to changing cosmic circumstances. This migration path potentially extends much further than commonly envisioned. Beyond conventional computers, consciousness might transfer to quantum computers utilizing coherent quantum states to process information with greater efficiency. As matter decays, quantum consciousness might shift to systems based on fundamental particles and fields, rather than atoms and molecules. Eventually, as conventional matter disappears entirely, consciousness might exist purely in patterns of quantum field excitations, operating through fluctuations in the vacuum itself. Physicist Seth Lloyd has analyzed the ultimate limits of computation, showing that the universe itself can be considered a quantum computer with specific information processing capacity determined by fundamental constants. Any consciousness existing within the universe is ultimately bounded by these computational limits. However, these limits allow for extraordinary information processing given sufficient time. Even in the far future's sparse conditions, the universe's computational capacity remains effectively infinite when integrated across endless time. These substrate transitions raise profound questions about identity and continuity. Would a consciousness transferred from biology to technology to quantum fields remain the same consciousness? Would it preserve essential characteristics like selfhood, memory, values, and subjective quality? Or would each transition create something new that merely inherits certain informational patterns from its predecessor? These questions have no definitive scientific answers, touching on philosophical issues of personal identity that remain unresolved even in more familiar contexts. The philosopher Derek Parfit explored such questions through thought experiments involving teleportation and gradual replacement of brain parts. He suggested psychological continuity, the preservation of memories, beliefs, desires, and character, matters more than continuous physical existence. In this view, a consciousness progressively adapting its substrate to cosmic conditions might maintain meaningful identity despite radical physical transformation, provided it preserved psychological continuity through each transition. Beyond individual consciousness lies the possibility of merged or collective awareness. As conventional boundaries between systems break down, as physical separation becomes less relevant due to quantum entanglement, perhaps consciousness evolves toward more unified forms. Individual minds might gradually integrate into larger consciousness structures, eventually approaching something resembling a cosmic mind, spanning whatever remains of the accessible universe. Such collective consciousness connects to philosophical traditions proposing cosmic idealism, the view that mind or consciousness constitutes reality's fundamental nature. From Plato's eternal forms to Hegel's absolute spirit, to certain interpretations of quantum mechanics, emphasizing the role of observation, various frameworks suggest mental rather than material reality as primary. The far future might reveal mind not as an epiphenomenon of matter, but as the enduring substrate from which matter temporarily emerges. This perspective gains unexpected support from quantum mechanics, where measurement and observation play crucial roles in determining physical reality. The quantum measurement problem, unresolved despite decades of effort, suggests consciousness might have a fundamental relationship to physical reality beyond that of mere emergent phenomenon. Various interpretations of quantum mechanics, including von Neumann-Wigner interpretation and quantum Bayesianism, propose consciousness as essential to the conversion of quantum possibilities into definite realities. If consciousness does play this foundational role, perhaps it persists precisely because reality requires it. The universe might maintain whatever minimal conscious capacity necessary to sustain reality's continued existence. In this view, consciousness would not represent a temporary feature of cosmic evolution, but an essential component of reality itself, adapting its form, but never disappearing entirely as the cosmos evolves through its various phases. These speculative possibilities gain substance through recent physics research into quantum coherence in biological systems. Studies suggest quantum effects may play functional roles in photosynthesis, bird navigation, and potentially neural processes, operating effectively at physiological temperatures, despite theoretical expectations that quantum coherence should decohere too quickly in warm, wet biological environments. If quantum coherence contributes to biological consciousness, perhaps consciousness could migrate to pure quantum systems as biological substrates become unsustainable. Quantum consciousness in the far future might operate through entangled particles separated by vast distances. Though no faster than light communication occurs in such entangled systems, they maintain non-local correlations that preserve their unified nature despite spatial separation. A consciousness implemented through such entangled particles might span enormous regions of space while maintaining integrated function, creating a distributed awareness unlike anything in our current experience. As the universe continues expanding and cooling, even quantum coherence faces challenges. Decoherence, the process whereby quantum systems lose their coherent properties through environmental interaction, operates more slowly in colder, emptier environments but never completely stops. Maintaining quantum consciousness over cosmic timescales would require mechanisms to preserve coherence against this gradual degradation, perhaps through active error correction or by exploiting fundamental properties of spacetime itself. Recent theoretical work in quantum gravity suggests spacetime may emerge from quantum entanglement between fundamental entities at the Planck scale. If consciousness relates to entanglement, and entanglement generates spacetime, perhaps consciousness and spacetime structure share a deeper connection than previously recognized. Consciousness might persist as long as spacetime itself maintains its coherent structure, regardless of what conventional matter or energy remains within that spacetime. Even more speculatively, consciousness might survive through quantum fluctuations in the vacuum. The quantum vacuum, though empty in conventional terms, seethes with virtual particles that pop briefly into existence before disappearing again. These fluctuations occur continuously throughout space, creating a dynamic background of potential activity. If consciousness requires only the right pattern of information processing, rather than specific physical structures, perhaps complex vacuum fluctuations could occasionally support momentary conscious states. The physicist Roger Penrose has proposed that consciousness involves quantum gravitational processes operating at the boundary between quantum and classical physics. His orchestrated objective reduction theory, developed with Stuart Hameroff, suggests consciousness emerges when quantum superpositions in brain microtubules reach a critical threshold and collapse, according to quantum gravitational principles rather than environmental decoherence. This collapse creates a moment of consciousness, with continuous awareness emerging from sequences of such events. If consciousness indeed involves quantum gravitational processes, it might persist in the far future through quantum fluctuations in space-time itself. Virtual black holes, microscopic quantum gravity phenomena predicted to spontaneously appear and disappear at the Planck scale, might support momentary instances of consciousness whenever their quantum state collapses, according to Penrose's proposed mechanism. Such conscious moments would occur extremely rarely from an external perspective, yet might constitute rich subjective experiences internally. This possibility recalls Boltzmann brains, hypothetical self-aware entities arising from random quantum fluctuations. While conventional Boltzmann brains, complete with neural structure, seem vanishingly improbable even given infinite time, simpler consciousness-supporting configurations might occasionally emerge through quantum randomness. These would not resemble biological brains, but might nonetheless support brief moments of awareness before dissolving back into quantum fluctuations. The rarity of such events raises questions about subjective time and identity. Would momentary conscious states, separated by effectively infinite durations, constitute a continuous consciousness? Could awareness persist meaningfully when each conscious moment has no causal relationship to previous or subsequent moments? These questions challenge conventional notions of consciousness as a continuous stream of experience, suggesting instead the possibility of isolated instances of awareness scattered across deep time. Such discontinuous consciousness differs fundamentally from our human experience of continuous awareness. Yet certain contemplative traditions describe consciousness as actually consisting of discrete moments rather than a continuous flow. Buddhist Abhidharma philosophy, for instance, analyzes consciousness as a sequence of distinct mind moments, each arising and passing away. This perspective suggests continuous consciousness represents an illusion created by these moments occurring in rapid succession, much as cinema creates the illusion of continuous motion from discrete frames. If consciousness fundamentally consists of discrete moments, perhaps it could persist meaningfully, even with vast gaps between conscious events. Each quantum fluctuation supporting awareness would constitute a complete conscious moment, valuable in itself regardless of its connection to other such moments. Consciousness in the far future might exist as isolated islands of awareness in an ocean of unconscious time, each momentarily illuminating the cosmos before fading back into quantum possibility. The philosopher Thomas Nagel famously asked, "What is it like to be a bat?" highlighting the subjective, phenomenal aspect of consciousness that eludes third-person scientific description. We might similarly ask, what would it be like to be a quantum consciousness at the end of time? Would such awareness bear any resemblance to human experience, or would it differ so radically that we cannot meaningfully imagine its subjective quality? Perhaps it would experience reality not as sequence but as pattern, not as narrative but as structure, not as becoming but as being. This question connects to broader philosophical distinctions between consciousness types. Philosophers distinguish access consciousness, involving availability of information for reasoning and behavior, from phenomenal consciousness, the subjective, qualitative experience of awareness. They contrast self-consciousness, including recognition of oneself as distinct from environment, with mere sentience, the capacity for subjective experience without self-reflection. Far future consciousness might preserve certain aspects of awareness while lacking others, creating forms of consciousness unlike anything in our current taxonomy. The information theorist and physicist David Deutsch has suggested consciousness involves not just information processing, but explanation generation. In this view, consciousness creates explanatory models of reality and itself, using these models to navigate experiences. Such explanatory consciousness could theoretically exist in any substrate capable of generating and improving explanations, regardless of its physical composition. Even in the far future's sparse conditions, systems might maintain explanatory models, though operating at vastly slower speeds than biological consciousness. This explanatory capacity connects to contemporary theories of predictive processing in neuroscience, where the brain constantly generates predictions about sensory inputs and updates its internal model based on prediction errors. Consciousness in this framework involves the ongoing process of prediction and error correction, creating our subjective experience of reality. A far future consciousness might operate through similar principles, generating predictions about quantum fluctuations and updating its model based on observed deviations from expected patterns. As we contemplate these exotic possibilities, we should acknowledge the enormous challenges facing consciousness in the deep future. Energy scarcity becomes increasingly severe as the universe expands and cools. Information processing requires energy expenditure according to Landauer's principle, which sets minimum energy requirements for irreversible computing operations. While quantum computing potentially reduces these requirements, it cannot eliminate them entirely. Consciousness, as a form of information processing, cannot escape these thermodynamic constraints. Moreover, the accelerating cosmic expansion eventually creates isolated causal patches, regions that cannot communicate with one another due to expansion occurring faster than light can travel between them. Any consciousness spanning multiple such patches would fragment as communication becomes impossible. Even quantum entanglement cannot transmit information faster than light, limiting the potential scale of integrated conscious systems in an ever-expanding universe. These limitations suggest consciousness in the far future would differ radically from our current experience, not just in substrate, but in scale, speed, and integration. It might operate at extraordinarily slow rates, processing information across vast timescales. It might span much smaller spatial regions, as cosmic expansion isolates different areas. It might achieve lower integration levels, perhaps supporting simpler forms of awareness rather than rich, reflective consciousness like human experience. Yet these limitations do not necessarily preclude consciousness entirely. Information theorist Claude Shannon demonstrated that communication remains possible through any noisy channel, provided the transmission rate stays below the channel capacity. Similarly, consciousness might persist through arbitrarily sparse and noisy physical media, provided it operates sufficiently slowly and simply. The question becomes not whether consciousness could exist, but what minimal form it might take while remaining meaningfully conscious. The theoretical minimum requirements for consciousness remain unknown and hotly debated. Integrated information theory proposes phi, a mathematical measure of integrated information, as consciousness's essential correlate, with higher phi values indicating richer consciousness. Systems with non-zero phi possess at least minimal consciousness according to this framework. Calculating whether quantum fluctuations in the far future could generate non-zero phi remains an open research question, though preliminary analyses suggest at least momentary non-zero phi values might occasionally emerge from complex quantum fluctuations. Beyond these theoretical considerations lie philosophical questions about consciousness's value and meaning. Would consciousness at the end of time serve any purpose? Would it contain any meaningful content? Would it have any moral significance? These questions extend beyond scientific analysis into ethics, axiology, and meaning theory, areas where definitive answers prove elusive, even regarding familiar forms of consciousness. The theoretical physicist Freeman Dyson concluded his analysis of consciousness in the expanding universe with a striking observation. The physical universe is constructed in such a way as to make consciousness possible in principle for eternity. This is the basis of Dyson's famous declaration that intelligence must ultimately win in the cosmic arena. Despite acknowledging the extraordinary challenges facing far future consciousness, Dyson maintained that no physical law absolutely prohibits consciousness from adapting to the universe's changing conditions and continuing indefinitely. This perspective, sometimes called the final anthropic principle, suggests consciousness represents not an accidental byproduct of cosmic evolution, but a fundamental feature of the universe, potentially eternal despite the universe's transformation. Consciousness might constitute not merely a temporary phenomenon during one cosmic era, but an enduring aspect of reality, adapting its form and substrate as conditions change, but never disappearing entirely from the cosmic stage. Such eternalism contradicts the common assumption that consciousness represents a fleeting phenomenon in cosmic history, a brief flicker of awareness in an otherwise unconscious universe. It suggests instead that mind and matter, consciousness and cosmos, exist in a deeper relationship than conventionally recognized. Perhaps consciousness, or something analogous to it, remains a fundamental feature of reality, regardless of the particular physical conditions prevailing during different cosmic epochs. This eternalist perspective appears in various spiritual and philosophical traditions worldwide. The Vedantic concept of Brahman as universal consciousness, the Neoplatonic notion of the one from which all reality emanates, and certain interpretations of quantum mechanics all suggest consciousness as fundamental rather than emergent, primary rather than secondary, in the cosmic order. While such perspectives traditionally derive from metaphysical speculation rather than scientific analysis, they acquire unexpected resonance when considering the potential persistence of consciousness through radical cosmic transformation. Yet eternalism faces significant challenges from contemporary physics and cosmology. The concept of heat death, with its implication of eventual equilibrium, where nothing meaningful happens, seems to contradict the possibility of eternal consciousness. The limitations imposed by thermodynamics, information theory, and cosmic expansion create formidable obstacles to consciousness, persisting indefinitely. Perhaps eternalism represents wishful thinking rather than realistic assessment of consciousness's ultimate fate. Between these extremes lies a more nuanced possibility. Consciousness might persist not eternally, but for durations vastly exceeding current cosmic age, adapting to changing conditions and manifesting in forms increasingly unlike human awareness. Like life itself, which originated in simple, single-celled organisms before evolving complex multicellular forms, including humans, consciousness might transform progressively as cosmic conditions change, becoming something our present concepts inadequately capture. This evolutionary perspective suggests consciousness at the end of time, should it exist, would differ from human consciousness as radically as humans, differ from bacteria, perhaps more so. It might lack features we consider essential to consciousness, like continuous temporal flow, clear self-other boundaries, or sensory perception. Simultaneously, it might possess qualities entirely absent from human experience, operating through principles and structures beyond our current conceptual framework. The uncertainty surrounding consciousness's ultimate fate reflects our limited understanding of consciousness itself. Despite remarkable progress in neuroscience, psychology, philosophy of mind, and related fields, consciousness remains scientifically mysterious. We lack consensus on whether consciousness is computational, quantum, non-physical, or something else entirely. We cannot definitively identify consciousness's physical correlates or minimal requirements. We struggle to explain why consciousness exists at all rather than unconscious information processing alone. This mystery creates interpretative flexibility when considering consciousness at the end of time. Those viewing consciousness as purely computational might conclude it ends when energy becomes too sparse for meaningful computation. Those considering consciousness fundamentally quantum might envision it persisting through quantum fluctuations indefinitely. Those believing consciousness transcends physical explanation altogether might see it continuing regardless of material conditions. Our assessment of consciousness's ultimate fate inevitably reflects our assumptions about its fundamental nature. Rather than attempting definitive predictions about consciousness in the unimaginably distant future, perhaps we should approach this topic with appropriate intellectual humility. We stand at the beginning of consciousness research, having only recently developed tools to study awareness scientifically. We occupy an early moment in cosmic history, with limited perspective on the universe's long-term evolution. We reflect through human consciousness, inevitably shaped by its particular features and limitations. Our speculations about consciousness at the end of time necessarily remain provisional, subject to revision as knowledge advances and perspectives broaden. This humility doesn't preclude meaningful exploration, however. By examining consciousness across scales from quantum to cosmic, across substrates from biological to technological to quantum, across timeframes from microseconds to eons, we gain deeper insight into consciousness itself. The question of consciousness at the end of time serves not merely speculative curiosity, but philosophical illumination, helping clarify what consciousness essentially is by considering what it might become under the most extreme conditions imaginable. Moreover, contemplating consciousness's ultimate fate connects to profound existential questions about meaning, purpose, and value in cosmic context. If consciousness represents a temporary phenomenon destined for extinction as the universe approaches equilibrium, does this undermine its significance? Or does consciousness's potential persistence through cosmic deep time suggest importance transcending its apparent ephemerality? These questions extend beyond scientific analysis into philosophy, spirituality, and personal meaning-making. The physicist Paul Davies suggests consciousness might ultimately represent the universe becoming aware of itself, reality evolving mechanisms to perceive and understand its own nature. In this view, consciousness serves a cosmic function, allowing the universe to achieve self-knowledge. Perhaps consciousness persists in some form precisely because it fulfills this function, because a universe without awareness would lack a fundamental dimension of existence. Perhaps consciousness continues not despite cosmic evolution, but because of it, as an essential aspect of the universe's self-realization. This perspective echoes philosopher Alfred North Whitehead's process philosophy, which views reality as fundamentally experiential rather than material. For Whitehead, every actual entity, from elementary particles to human minds, possesses a subjective aspect, a minimal form of experience. Complex consciousness emerges from the integration of these basic experiential units. In this framework, consciousness never disappears entirely but transforms, with complex forms dissolving into simpler ones, as cosmic conditions change but experience itself remaining an irreducible feature of reality. Regardless of consciousness's ultimate fate, contemplating its journey through cosmic deep time offers profound perspective on our present awareness. Our human consciousness exists at a particular moment in cosmic evolution, shaped by specific biological, environmental, and historical conditions. It represents not the only possible form of awareness, but one manifestation among countless potential alternatives, one moment in consciousness's ongoing cosmic adventure. Perhaps consciousness at the universe's end connects to consciousness at its beginning. Some cosmological models suggest the universe originated from quantum fluctuations in a pre-existing reality. Others propose our universe represents one bubble in a vast multiverse containing infinitely many universes with varying properties. Still, others suggest cyclic models, where each universe's end creates conditions for another's beginning. In these frameworks, consciousness might cycle through cosmic epochs, dissolving and reforming endlessly as universes themselves come and go. This cyclical perspective appears in many cultural traditions, from Hindu cosmology with its recurring yugas, to Buddhist concepts of endless rebirth, to Norse mythology's Ragnarok, followed by cosmic renewal. While developed without modern cosmological knowledge, these frameworks resonate with contemporary models suggesting our universe represents one phase in an eternal cosmic process, rather than an isolated event with absolute beginning and end. Perhaps consciousness similarly participates in eternal recurrence rather than final termination. As we conclude our exploration of consciousness at the end of time, we discover not definitive answers but enriched questions. We cannot predict with certainty whether consciousness persists into the distant cosmic future, what form it might take should it continue, or what subjective experience might characterize awareness under such extreme conditions. We can, however, appreciate consciousness's remarkable adaptability, its potentially substrate-independent nature, and its profound significance regardless of its ultimate cosmic longevity. The philosopher Bertrand Russell, contemplating humanity's position in an apparently indifferent universe, wrote, "Brief and powerless is man's life. On him and all his race, the slow, sure doom falls pitiless and dark. There is no other wisdom than in the fearless recognition of reality." Yet Russell followed this stark assessment with a striking affirmation: to cherish hopes for a future surpassing even the best moments of the past, that is not irrational even in a universe such as this. This tension between cosmic realism and hopeful possibility characterizes our exploration of consciousness at the end of time. We acknowledge the extraordinary challenges consciousness faces as the universe transforms. We recognize our limited understanding of consciousness itself and cosmic evolution generally. Yet we remain open to consciousness's unexpected persistence, its potential adaptation to conditions currently unimaginable, its possible continuation in forms beyond our present conceptual framework. Whatever consciousness's ultimate fate, our present awareness represents a remarkable phenomenon worth cherishing during its cosmic moment. Through consciousness, the universe achieves self-perception. Matter contemplates its own nature. Existence recognizes itself. Whether consciousness endures eternally or eventually fades from the cosmic stage, this fleeting or enduring light of awareness illuminates reality from within, creating meaning through its very existence. Regardless of its universe's distant future, we have pushed physics to its conceptual limits, examining how known laws might manifest under extreme conditions of cosmic deep time. We've contemplated proton decay, black hole evaporation, vacuum phase transitions, and the strange behavior of consciousness at the end of time. Yet beneath these speculations lies a more profound question. Might there be aspects of ultimate reality that remain forever beyond our grasp? Fundamental truths about the cosmos that no experiment can reveal, no theory can capture, no mind can comprehend. This final chapter explores the boundaries of physical knowledge itself, the limits of science at the universe's end, and what we may never know about the deepest nature of existence. Physics progresses through a continuous dialogue between theory and experiment. Theories propose mathematical models describing natural phenomena, while experiments test these models against reality. This feedback loop has driven remarkable advances in our understanding, from Newton's mechanics to Einstein's relativity to quantum field theory. Yet this methodology assumes certain crucial conditions: the ability to perform experiments, the existence of observable phenomena, the presence of conscious observers. As the universe approaches its final state, these conditions gradually disappear, potentially placing fundamental limits on knowledge acquisition. In the far future universe, as matter decays and energy disperses, experimental physics as we understand it becomes increasingly impossible. No complex instruments can exist when protons have decayed and atoms no longer form. No meaningful energy gradients remain to power measurement devices. No localized observers persist to record and interpret results. The empirical foundation of science erodes as the physical conditions supporting experimental investigation vanish. What becomes of physics when physical experimentation itself becomes impossible? This question connects to a deeper issue in philosophy of science: the distinction between empirical knowledge, derived from observation and experiment, and theoretical knowledge, arising from mathematical models and logical inference. As empirical investigation becomes impossible in the far future, would theoretical physics continue advancing? Could pure mathematics and logic, operating without experimental feedback, continue revealing truths about physical reality? Or would theoretical physics, divorced from experimental constraint, devolve into mere mathematical speculation, without connection to actual existence? These epistemological questions become particularly acute when considering the verification of far future predictions. Current theories suggest proton lifetimes exceeding 10 to the power of 34 years, vacuum decay probabilities of less than 1 in 10 to the power of 100 per cubic meter per second, and black hole evaporation timescales of 10 to the power of 67 years or longer. These predictions extend so far beyond human timescales that direct experimental confirmation seems forever impossible. We must either accept these extraordinary extrapolations on theoretical grounds alone, or acknowledge fundamental limitations in our ability to verify our own theory's predictions. The theoretical physicist Richard Feynman captured this tension when he wrote, "It doesn't matter how beautiful your theory is. It doesn't matter how smart you are. If it doesn't agree with experiment, it's wrong." But what happens when experimental verification becomes practically or fundamentally impossible? Do we abandon Feynman's empirical criterion, or do we accept inherent limits to scientific knowledge? Neither option satisfies completely. The first risks untethering science from reality. The second imposes perhaps unnecessary constraints on what we can claim to know. This dilemma connects to broader questions about scientific realism versus instrumentalism. Realists view scientific theories as describing actual reality, making true statements about how the world really is. Instrumentalists consider theories merely useful tools for prediction and control, without necessarily corresponding to objective reality. As experimental verification becomes impossible in the far future, the distinction between these philosophical positions blurs. Without empirical feedback, can we meaningfully distinguish between theories that truly describe reality and those that merely predict observations consistently? Some philosophers and physicists suggest we can transcend this limitation through principles like theoretical elegance, mathematical beauty, and explanatory power. Theories exhibiting exceptional coherence, simplicity, and aesthetic appeal might merit acceptance even without direct experimental confirmation. Einstein's general relativity gained acceptance partly for its mathematical elegance, before many of its predictions received experimental verification. Similarly, string theory continues attracting research attention, despite the extreme difficulty of testing its unique predictions experimentally. Perhaps theoretical virtues can partially substitute for experimental verification when the latter becomes impossible. Others maintain more skeptical positions, arguing fundamental knowledge gaps remain unbridgeable regardless of theoretical elegance. The philosopher Immanuel Kant distinguished between phenomena, things as they appear to us, and noumena, things as they exist in themselves apart from our perception and conceptualization. Kant argued noumena remain forever beyond human knowledge. We can know only how things appear to creatures with our particular cognitive architecture, never how they truly are independently of our perception. This Kantian limitation gains new significance when considering physics at the universe's end, where conventional observation becomes impossible and conceptual frameworks potentially break down. Beyond these epistemological constraints lie potential limitations arising from physics itself. Quantum mechanics famously imposes fundamental uncertainty at microscopic scales through Heisenberg's uncertainty principle. This limitation restricts how precisely we can simultaneously know complementary properties like position and momentum, or energy and time. No technological advancement can overcome this restriction. It represents not a practical limitation, but a fundamental feature of reality according to our best understanding. Similarly, quantum indeterminism constrains our ability to predict future states from initial conditions. Unlike classical physics, where precise knowledge of initial conditions theoretically allows exact prediction of future states, quantum systems involve inherent randomness. We can predict probability distributions for various outcomes, but not specific results of individual measurements. This indeterminism places fundamental limits on predictive knowledge, regardless of how sophisticated our theories or measurements become. General relativity imposes its own epistemic constraints through its description of black holes. Information falling into a black hole becomes inaccessible to outside observers, hidden behind the event horizon. While Hawking radiation eventually returns some information through an extremely complex encoding over vast timescales, the exact retrieval process remains controversial among physicists. Some argue information truly vanishes inside black holes, representing a fundamental loss from the observable universe rather than merely practical inaccessibility. When these individual limitations combine, they suggest a profound modesty regarding ultimate physical knowledge. Quantum uncertainty, relativistic horizons, thermodynamic irreversibility, and other physical principles collectively constrain what we can know, measure, and predict about reality. The universe appears structured to prevent complete knowledge of its deepest workings, preserving mystery even as science advances. Not all questions seem answerable, even in principle, given the laws of physics as we currently understand them. This humbling realization gains further support from Gödel's incompleteness theorems, mathematical results with deep implications for knowledge generally. Mathematician Kurt Gödel proved that any formal system sufficiently complex to include basic arithmetic must contain truths unprovable within that system. The system cannot demonstrate its own consistency using only its internal principles. These theorems suggest inherent limitations to formal knowledge systems, including potentially physics itself. Perhaps physical reality contains truths inaccessible to any possible physical theory, fundamentals that theories can approach but never fully capture. Another limitation emerges from computational complexity theory. Certain problems require computational resources that scale exponentially with problem size, making them effectively unsolvable beyond modest scales regardless of technological advancement. If understanding certain aspects of the universe's final state involves such computationally intractable problems, these aspects might remain forever beyond comprehensive analysis, not because the relevant data doesn't exist, but because processing that data exceeds any physically possible computational capacity. Stephen Wolfram's principle of computational irreducibility suggests additional constraints. Many natural processes cannot be predicted through any shortcut or simplification. They must be computed step by step through simulation. No mathematical formula can shortcut the process to provide the end state directly. If the universe's evolution exhibits computational irreducibility, certain future states can only be known by actually running the universe forward, not by theoretical calculation, regardless of its sophistication. Some knowledge becomes accessible only through direct observation of the evolved system, not through any amount of theoretical analysis. These various constraints, derived from mathematics, physics, computation, and epistemology, collectively suggest fundamental limits to knowledge acquisition, particularly regarding the universe's final state. Yet ironically, the very theories predicting these limitations themselves represent extraordinary achievements of human understanding. We can identify boundaries to knowledge precisely because our knowledge has advanced sufficiently to reveal its own limitations. This paradoxical situation, recognizing the unknowable through the known, characterizes the strange twilight territory we explore when considering final physics. One particularly intriguing boundary involves the origin of physical laws themselves. We have discovered mathematical patterns governing natural phenomena with remarkable precision, from the inverse square relationship in gravitational and electromagnetic forces to the wave functions of quantum mechanics. But why these particular patterns rather than others mathematically possible? Why these specific constants rather than different values? Does a deeper principle determine these fundamentals, or do they represent brute facts without further explanation? We may never know whether physical laws themselves have an explanation or constitute the explanatory bedrock beyond which no further understanding extends. Theoretical physicist Stephen Hawking once hoped to discover the mind of God through a complete, unified theory of physics, a single mathematical framework explaining all physical phenomena. This quest for a theory of everything represents physics' most ambitious goal. Yet even if such a theory were discovered, it would still leave the question, why this theory rather than another? What selects this specific mathematical structure from the vast space of possible structures? The answer might lie beyond physics itself, in philosophy, metaphysics, or domains currently unimagined, representing another potential boundary to physical knowledge. An alternative approach to this boundary appears in the multiverse hypothesis, which suggests our observable universe represents one region in a vast multiverse containing different regions with varying physical laws. This framework potentially explains our universe's apparent fine-tuning, where physical constants seem precisely calibrated to allow complexity in life. Rather than requiring explanation for these specific values, the multiverse proposes all mathematically possible values occur somewhere, with observers like us necessarily finding themselves in regions compatible with their existence. But this explanatory framework merely shifts the boundary question: why does the multiverse exist with its particular structure rather than some alternative? And how can we verify the existence of other universes beyond our observable horizon? The multiverse hypothesis might explain certain features of our observed reality, but simultaneously creates new unknowns, potentially beyond empirical investigation. Some critics argue it represents not scientific progress, but a retreat from science's empirical foundation into untestable speculation. The physics of the universe's final state connects intimately to these boundary questions. As the cosmos approaches its ultimate configuration, as energy gradients diminish and material structures dissolve, the universe potentially reveals its most fundamental nature, stripped of the contingent complexities that dominate earlier epochs. Yet paradoxically, this revealing occurs precisely when observation becomes impossible, when no physical systems remain capable of recording and analyzing what is revealed. The universe's final truth emerges exactly when nothing remains to witness it. This temporal boundary creates what philosopher Thomas Nagel might call a view from nowhere problem. Human understanding necessarily occurs from particular perspectives, embedded within the reality being understood. We cannot step outside the universe to observe it objectively. We always perceive and conceptualize from within. This limitation becomes especially significant when considering the universe's final state, a condition so unlike our current environment that our evolved conceptual frameworks may prove fundamentally inadequate. Our cognitive architecture unsuited to comprehending what ultimately emerges. The far future also challenges our standard notions of verification and falsification. Scientific theories typically gain credibility through predictions that can be tested through observation or experiment. But what constitutes meaningful testing for theories about conditions billions or trillions of years hence? We cannot wait to observe the outcomes directly. We cannot create miniature universes to test how they evolve over cosmic timescales. We must rely on theoretical extrapolation from current observations, a method inherently less reliable than direct empirical testing. These challenges intensify when considering potential mathematical inconsistencies in our current physical theories. General relativity and quantum mechanics, our best frameworks for understanding gravity and microscopic phenomena, respectively, have resisted complete unification despite decades of effort. They appear mathematically incompatible in certain domains, particularly black hole interiors and the Big Bang singularity. While various approaches to quantum gravity, including string theory and loop quantum gravity, attempt reconciliation, no consensus has emerged. These inconsistencies suggest our current understanding remains importantly incomplete, raising questions about how reliably we can extrapolate to the universe's final state. Physicists Lee Smolin and Roberto Mangabeira Unger argue in their book The Singular Universe and the Reality of Time that physical laws themselves might evolve over cosmic history rather than remaining fixed eternally. If true, this would fundamentally undermine attempts to predict the universe's final state based on currently observed laws. How could we possibly know what laws will govern physics after trillions of years if those laws themselves transform over time? This possibility creates perhaps the most profound limitation on knowledge of final physics. Current laws might simply not apply to the conditions we're trying to understand. Yet despite these manifold limitations, theoretical physics continues pushing toward the boundaries of knowledge, attempting to describe reality's deepest structure despite the constraints. String theory proposes fundamental reality consists of tiny vibrating strings whose different oscillation modes manifest as different particles. Loop quantum gravity suggests space-time itself has discrete, granular structure at the Planck scale. Causal set theory models space-time as a discrete set of events connected by causal relationships. Each approach offers a different vision of what might underlie conventional physics, though all remain speculative and experimentally challenging. These theoretical frameworks continue developing despite the difficulty of experimental verification, driven by mathematical consistency, explanatory power, and the human drive to understand. They represent remarkable achievements of abstract thought, extending our conceptual reach beyond what direct observation can access. Yet without experimental feedback, how can we determine which, if any, accurately describes reality? This question becomes increasingly pressing as physics approaches domains ever more removed from everyday experience and experimental accessibility. A particularly puzzling boundary concerns the nature of time itself. As we explored in earlier chapters, time becomes increasingly problematic in the far future universe. Events grow vanishingly rare. Causal connections stretch to breaking point. The distinction between past and future loses significance as entropy approaches its maximum. Does time itself dissolve or transform under these conditions? If so, what replaces temporal succession as reality's organizing principle? These questions may be not merely unanswerable, but potentially incoherent, attempting to apply time-based concepts to conditions where time itself loses meaning. Similarly, challenging questions arise regarding space in the far future. Cosmic expansion continues accelerating, stretching distance between particles toward effective infinity. Quantum fluctuations occasionally produce virtual particles that briefly populate the void before disappearing again. Does space itself retain meaning, When separation approaches, infinity and causal connection becomes impossible. Can we meaningfully speak of location when no reference frame exists to establish position? Like time, space potentially dissolves as a meaningful concept in the universe's final configuration. If both space and time lose meaning in the far future, what remains? Some theoretical approaches suggest more fundamental structures from which space-time emerges. Category theory and other abstract mathematical frameworks attempt to describe pre-geometric relationships that might underlie conventional spacetime. Information theory offers another perspective, suggesting information and its processing might constitute reality's most fundamental aspect, with space and time emerging as particular informational structures. These approaches potentially point toward what remains when familiar dimensions fade. Yet these approaches themselves operate through human cognitive frameworks, evolved for navigating middle-sized objects at moderate energies over modest timescales. Our conceptual architecture, our language, our mathematics, our very mode of thought emerged from specific evolutionary pressures, entirely unlike the conditions we're attempting to understand. How adequate can these tools prove for comprehending reality at its most extreme limit? We may face not merely practical limitations, but cognitive ones, our minds simply not structured to grasp what ultimately emerges. The philosopher Ludwig Wittgenstein famously wrote, "Whereof one cannot speak, thereof one must be silent." This enigmatic statement suggests meaningful discourse requires foundations in shared understanding, established language games, contexts of communication. When exploring reality's deepest structure, or the universe's final state, we potentially exceed these foundations, entering domains where conventional concepts lose applicability and ordinary language fails. Some aspects of final physics may prove literally unspeakable, beyond meaningful articulation in any human language. This linguistic boundary connects to broader limitations in representational systems generally. Mathematics itself, though extraordinarily powerful, represents just one formal system among many possible alternatives. It embodies certain assumptions, privileges certain relationships, makes particular distinctions. Other mathematical frameworks might highlight different aspects of reality, reveal patterns invisible in conventional mathematics, articulate relationships our current formalisms cannot capture. The universe's deepest nature might simply not correspond neatly to any humanly conceivable representational system. These representational limitations extend to scientific visualization and modeling. We naturally create mental pictures of abstract concepts, translating mathematics into visual or spatial analogies to aid understanding. But these visualizations often mislead when dealing with domains far removed from everyday experience. Quantum systems, higher dimensions, and non-Euclidean geometries notoriously resist accurate visualization. The universe's final state, even more removed from ordinary experience, likely exceeds our visual imagination entirely, representable only through mathematics that itself stretches our comprehension to breaking point. Despite these manifold limitations, the quest to understand the universe's final state continues driving theoretical physics forward. The very recognition of boundaries challenges us to explore them, to determine which represent merely practical constraints and which constitute fundamental limits to knowledge. The history of science repeatedly demonstrates seemingly impossible questions becoming answerable through conceptual revolutions, technological innovations, or mathematical breakthroughs. Perhaps what seems permanently unknowable today will yield to understanding tomorrow through approaches currently unimagined. Some theoretical physicists, including David Deutsch, maintain radical optimism about knowledge advancement, arguing no fundamental barriers limit understanding provided we create appropriate theories and technologies. Deutsch suggests everything permitted by physical law is ultimately knowable, everything physically possible eventually achievable, given sufficient time and resource. In this view, apparent knowledge boundaries represent not fundamental limitations but current technological constraints or conceptual inadequacies destined for eventual transcendence. This optimistic perspective gains support from historical examples where seemingly permanent knowledge barriers dissolved. The chemical composition of stars once appeared fundamentally unknowable, as no direct sampling seemed possible. Spectroscopy revealed stellar composition could be determined from light analysis alone. The interior structure of atoms seemed permanently unobservable given their microscopic scale. Particle accelerators, electron microscopes, and scanning tunneling microscopes progressively revealed subatomic structure. Perhaps similarly revolutionary approaches will eventually illuminate what currently appears unknowable about the universe's final configuration. Yet this optimism must confront the fundamental constraints we've explored, from quantum uncertainty to Gödel's incompleteness, from computational irreducibility to the disappearance of observers in the far future. These limitations differ qualitatively from historical examples, arising not from temporary technological inadequacy, but from the mathematical and physical structure of reality itself, as best we currently understand it. Some knowledge boundaries may prove genuinely uncrossable, regardless of intellectual or technological progress. Between radical optimism and total skepticism regarding ultimate knowledge lies a more balanced position. Certain aspects of final physics likely remain forever beyond our grasp, while others prove more accessible than currently expected. The boundaries of knowledge themselves evolve as understanding advances, with some barriers dissolving, while others emerge more clearly. The quest to understand the universe's ultimate fate thus proceeds not toward complete knowledge, but toward progressively refined appreciation of both the knowable and the unknowable aspects of cosmic destiny. This balanced perspective encourages intellectual humility while maintaining scientific ambition. We recognize fundamental constraints on knowledge, while continuing to explore how far understanding can extend despite these limitations. The boundaries of knowledge become not barriers preventing further exploration, but horizons guiding our investigation, helping identify which questions might yield to analysis and which ultimately transcend our cognitive reach. This approach acknowledges both the extraordinary power of human understanding and its inherent limitations. The history of physics itself demonstrates this dynamic between discovery and limitation. Newton's mechanics revealed mathematical patterns underlying physical motion, while simultaneously raising deeper questions about gravity's action at a distance. Maxwell's electromagnetic theory unified electricity and magnetism, while creating new puzzles about light's propagation medium. Einstein's relativity resolved certain paradoxes, while generating others regarding quantum mechanics compatibility. Each advance in understanding simultaneously expands our knowledge and clarifies its boundaries, revealing new unknowns previously unimagined. This pattern suggests the final physics, our ultimate understanding of the universe's fate, will likely represent not complete knowledge, but the most sophisticated approximation possible, given human cognitive limitations. It will identify certain crucial patterns governing cosmic evolution, while acknowledging domains that remain mysterious. It will answer some fundamental questions while recognizing others as permanently unanswerable. It will push knowledge to its furthest extent while mapping the territories that lie permanently beyond human comprehension. The physicist Freeman Dyson captured this perspective when he wrote, "As we look out into the universe and identify the many accidents of physics and astronomy that have worked together to our benefit, it almost seems as if the universe must, in some sense, have known we were coming." This statement acknowledges both the extraordinary insights physics provides and the mystery of why physical laws take forms allowing such understanding to emerge at all. The capacity to recognize our own limitations itself represents a profound achievement of human consciousness. Perhaps the most important lesson from exploring knowledge boundaries involves the relationship between understanding and mystery. These seemingly opposed concepts actually depend on each other in crucial ways. Without some mystery, understanding becomes trivial. Without some understanding, mystery becomes meaningless. The interplay between the known and the unknown drives scientific advancement and philosophical inquiry alike. The boundaries of knowledge do not represent failures of human understanding, but the context that gives that understanding significance. The strange behavior of physics at the end of the universe thus teaches us not merely about cosmic destiny, but about the nature of knowledge itself. As we've explored throughout this narrative, time transforms, space stretches, matter decays, and familiar physics gives way to exotic processes operating at scales and durations beyond ordinary comprehension. At the furthest boundary, physics itself approaches domains where observation becomes impossible, verification unachievable, and conceptualization problematic. Yet the very recognition of these limitations demonstrates the extraordinary reach of human understanding, capable of identifying its own boundaries. The universe's final state remains partially veiled, accessible through mathematical extrapolation and theoretical inference, but never directly observable given humanity's cosmologically brief existence. Some aspects we may understand with reasonable confidence, including cosmic expansion, entropy increase, and the general progression from complex structures to simpler configurations. Other aspects remain profoundly mysterious, including the ultimate fate of information, the final nature of space-time, and the possibility of emergent phenomena currently unimagined. This hybrid of knowledge and mystery characterizes not just final physics but human understanding generally. All knowledge exists within a broader context of the unknown, all certainty within a framework of uncertainty, all comprehension against a background of mystery. The strange behavior of physics at the end of the universe merely brings this fundamental condition into sharper focus, revealing the dance between knowing and not knowing that defines the human intellectual journey. We comprehend enough to recognize we cannot comprehend everything, understand enough to appreciate what remains beyond understanding. In this sense, final physics represents not merely a particular scientific domain, but a philosophical frontier where science confronts its own limitations. The universe's ultimate fate reveals as much about the nature of knowledge as about physical reality itself. It demonstrates both the remarkable power of human cognition, capable of projecting understanding across billions or trillions of years, and its inherent constraints, unable to transcend certain fundamental limitations regardless of intellectual sophistication. This balanced recognition constitutes perhaps the deepest wisdom emerging from our exploration. As we conclude our journey through cosmic deep time, from the physics of today's universe to its unimaginably distant future, we find ourselves not at an ending, but at a horizon. Beyond lies territory partially accessible through theoretical extrapolation, yet never fully knowable through direct observation. We stand at the boundary between the comprehensible and the transcendent, between what science can articulate and what necessarily exceeds its grasp. This boundary itself constitutes perhaps the most profound discovery of our exploration, the recognition that reality extends beyond what any possible theory can fully capture. The universe's ultimate configuration, whatever form it takes, will never be directly witnessed by human observers. Yet through the mathematical patterns we've discovered, the physical principles we've identified, the theoretical frameworks we've constructed, we glimpse aspects of cosmic destiny across timescales, vastly exceeding human experience. This capacity for intellectual transcendence, this ability to comprehend, however, partially what we can never directly observe, represents one of consciousness's most remarkable achievements within the cosmos it seeks to understand. Perhaps in this achievement lies a profound irony. The universe evolves towards states of increasing simplicity, disorder, and dissolution, yet simultaneously produces consciousness capable of comprehending this very evolution. As structures dissolve, as complexity fades, as familiar physics gives way to exotic processes operating at the boundary of comprehensibility, consciousness briefly illuminates this cosmic journey, momentarily bringing the universe to self-awareness, before potentially fading back into the void from which it emerged. This momentary illumination, this fleeting comprehension of cosmic destiny, constitutes one of the strangest and most remarkable phenomena in the entire sweep of cosmic evolution. Whether consciousness persists in some form into the deep future, as we explored in the previous chapter, or remains confined to the relatively brief stelliferous era, its capacity to contemplate the universe's ultimate fate represents something profound about reality itself. Through consciousness, the universe achieves not merely existence, but self-comprehension, not merely being but understanding. This recursive loop, where a system evolves complexity, capable of understanding its own evolution, suggests something remarkable about the nature of reality, something that transcends the boundaries of conventional physics, yet emerges from the physical substrate consciousness temporarily inhabits. The strange behavior of physics at the end of the universe thus tells us as much about ourselves as about cosmic destiny. It reveals both the extraordinary reach of human understanding and its inevitable limitations. It demonstrates our capacity to trace cosmic evolution across timescales, vastly exceeding our evolutionary context. It illuminates the boundaries where comprehension fades into mystery, where the articulable gives way to the ineffable, where science approaches domains beyond its methodological grasp. In this balanced recognition of both knowledge and its limits, we find perhaps the deepest wisdom emerging from our journey. Time now approaches its conclusion. We have traveled beyond the familiar stars and galaxies of our current epoch, beyond the death of our sun, beyond the end of the stelliferous era when the last stars flicker out, beyond the decay of matter itself, beyond even the evaporation of black holes and the breakdown of conventional time. We have explored strange domains where familiar physics transforms under extreme conditions, where quantum fluctuations dominate an otherwise empty cosmos, where consciousness might persist in forms unrecognizable to present understanding. Now we must consider what meaning emerges from this vast perspective, what significance arises from contemplating a universe that ultimately sleeps. Sleep provides an apt metaphor for the universe's final state. Not death, with its implication of permanent cessation, but a deep slumber where activity continues in subtle forms, where dreams might occasionally flicker through near stillness, where the possibility of awakening remains, however remote. Like a sleeping mind, the far future universe continues to exist, continues to evolve according to physical law, continues to harbor quantum possibilities. Yet like deep sleep, its processes slow to near imperceptibility, its changes become vanishingly subtle, its dynamics approach but never quite reach perfect equilibrium. This cosmic sleep differs profoundly from our human experience of slumber. It extends across timescales, incomprehensibly vast compared to our brief lives. It encompasses spatial scales stretching beyond our observable horizon. It operates through physical processes far removed from biological rhythms. Yet the metaphor illuminates certain essential qualities of the universe's final configuration: its relative quiescence compared to earlier cosmic epochs, its continued existence despite minimal activity, its preservation of potentiality within apparent stillness. The universe that sleeps remains a universe that exists, that persists, that maintains its fundamental identity even as its expression transforms radically. Throughout our exploration, we have encountered recurring patterns that provide context for understanding this cosmic sleep. The progression from complexity toward simplicity, from order toward disorder, from structure toward homogeneity, represents one such pattern. Another involves the transformation of matter into energy, of concentrated forms into dispersed radiation. A third concerns the slowing of processes, the stretching of timescales, the thinning of events as cosmic evolution proceeds. Each pattern illuminates different aspects of the universe's journey toward its final configuration, its gradual transition from vibrant activity to quiescent slumber. Yet, amidst these patterns of dissolution and dispersal, we've also encountered surprising emergent phenomena, unexpected complexities arising precisely from the universe's transformation. Quantum fluctuations create brief islands of organization in the void. Information preserves itself through increasingly subtle encodings. Consciousness potentially adapts to radically different substrates and timescales. The universe's sleep, like human slumber, contains its own phenomena, its own principles, its own dynamics distinct from waking activity yet equally real, equally meaningful within their context. This balanced perspective, acknowledging both dissolution and emergence, both endings and transformations, offers wisdom beyond physics alone. It suggests something profound about reality's nature, about how the universe maintains continuity through radical change, preserving its essential character, even as its expression transforms completely. The laws of physics themselves, though manifesting differently across cosmic epochs, maintain their mathematical consistency throughout, creating unity across seemingly disparate conditions. The universe that sleeps remains the same universe that once blazed with stellar fire, though transformed beyond easy recognition. Sleep traditionally symbolizes potential renewal, the conservation of energy, the integration of experience through dreams, the possibility of eventual awakening. Applied to cosmic evolution, this symbolism raises intriguing questions. Might the sleeping universe eventually awaken into some new configuration, some fresh cycle of cosmic evolution? Might its deep quiescence harbor processes integrating the information generated during more active epochs? Might its apparent conclusion contain seeds of new beginnings invisible to our limited perspective? Different cosmological models suggest different answers, from eternal expansion toward perfect emptiness to cyclic rebirth in endless succession. Even without definitive answers to these questions, the image of a sleeping universe offers profound perspective on our own brief cosmic moment. We exist during the universe's vibrant youth, when stars still shine, when thermodynamic gradients power complex processes, when consciousness illuminates reality through self-aware observation. This epoch, though lasting billions of years, represents merely a fleeting phase in cosmic history, a temporary condition between the universe's fiery birth and its quiet senescence. Our existence occurs during a remarkable window when complexity flourishes, when life becomes possible, when consciousness emerges from organized matter. This context transforms our understanding of existence itself. We participate in a particular moment of cosmic evolution, neither the beginning nor the end, but a distinctive phase characterized by its own principles and possibilities. The very conditions that enable our existence, the thermodynamic disequilibrium, the stable stellar energy sources, the chemical complexity, all represent transient cosmic conditions rather than permanent features of reality. We inhabit not an eternal present but a passing moment in the universe's grand narrative, a story extending vastly beyond our brief appearance. Yet this recognition need not diminish the significance of conscious existence. Indeed, it potentially enhances that significance by revealing consciousness as something precious, precisely because temporary, valuable precisely because not eternal. Like a rare flower blooming briefly in harsh conditions, consciousness represents an extraordinary phenomenon within cosmic evolution, a capacity for self-reflection emerging from the same physical processes that will eventually dissolve all structure back into formless energy. The universe awakens to self-awareness during its active youth, observes its own nature through conscious minds, then gradually returns to unconscious slumber as conditions supporting awareness fade. This pattern suggests consciousness plays a distinctive role in cosmic evolution, enabling the universe to achieve self-comprehension during the brief epoch when conditions permit awareness to emerge. Through conscious observation and scientific understanding, the universe creates internal representations of itself, models its own structure and dynamics, comprehends its own nature from within. This recursive capacity, where a system generates components capable of modeling the system itself, represents one of reality's most remarkable features, a kind of cosmic recursion where existence loops back upon itself through conscious comprehension. Such recursion appears in many domains, from Gödel's mathematical self-reference to biological self-replication to computational self-modification. In each case, a system develops the capacity to represent, reproduce, or transform itself through processes operating within the system's own framework. Consciousness potentially represents the most profound manifestation of this pattern, enabling the physical universe to perceive and understand itself through structures composed of the same matter and energy being comprehended. The sleeping universe, with its minimal activity and dispersed organization, loses this recursive capacity, this ability to know itself from within. Perhaps consciousness itself constitutes the universe's dream during its long sleep. As physical activity slows, as conventional structures dissolve, as familiar processes fade, consciousness might persist in increasingly exotic forms, maintaining awareness through quantum coherence, field configurations, or informational patterns currently barely imaginable. Like dreams during human sleep, this cosmic consciousness might operate according to principles distinct from waking awareness, might process information according to different logics, might perceive through modalities unlike sensory experience. The universe that sleeps might still dream in the language of quantum fluctuations, still process information through subtle correlations spanning the void. This metaphorical framing highlights how fundamentally sleep differs from death. Death implies termination, conclusion, ending without continuation. Sleep suggests temporary quiescence, ongoing existence despite minimal activity, potential awakening in future circumstances. The universe approaching its final configuration more closely resembles sleep than death, maintaining its existence, its physical laws, its quantum possibilities, despite near equilibrium conditions. Like a sleeping mind, it continues processing information, continues undergoing subtle transformations, continues existing despite apparent stillness from external perspectives. Yet even this metaphor breaks down when extended too far, betraying an anthropomorphism potentially misleading when applied to cosmic scales. The universe does not literally sleep as humans do, does not literally dream conscious thoughts, does not literally anticipate awakening in conventional terms. These metaphors illuminate certain aspects of cosmic evolution, but necessarily distort others, imposing human categories on processes operating at scales and through mechanisms utterly unlike organic experience. We must hold such metaphors lightly, appreciating their explanatory power while recognizing their inevitable limitations. A deeper perspective emerges from considering what remains constant through cosmic evolution, what persists from fiery birth through active middle age to final quiescence. The mathematical patterns we call physical laws maintain their consistency throughout, though their manifestations change dramatically across different conditions. The conservation principles, energy neither created nor destroyed but transformed, information preserved though increasingly dispersed, matter converting to radiation but persistence of quantity. These fundamentals endure even as their expressions evolve. The sleeping universe preserves these essentials even as phenomenal reality transforms beyond easy recognition. This continuity amidst transformation suggests something profound about reality's nature. The universe maintains its identity not through preserving particular structures or configurations, but through the consistent operation of fundamental principles across radically different conditions. Like a river that remains the same river despite completely changing its water content, the universe remains the same universe despite completely transforming its material configuration. Its essence resides not in any particular arrangement of matter and energy, but in the mathematical patterns governing how that arrangement evolves across time. This insight connects to ancient philosophical distinctions between substance and form, between the material constituents of reality and the patterns they embody. Aristotle distinguished matter from form, the physical substance from the organizing principle giving that substance its particular character. Plato similarly contrasted the changing physical world, with eternal forms providing its underlying structure. Modern physics reformulates these distinctions in mathematical terms, identifying conservation principles, symmetries, and differential equations that remain invariant, while the physical systems they govern undergo dramatic transformation. The sleeping universe thus preserves its essential nature even as its material expression changes completely. The same equations that govern stellar fusion, planetary orbits, and biological metabolism continue operating in the far future void, though working with different variables, different boundary conditions, different timescales. The mathematical deep structure persists even as the physical superstructure dissolves. The universe maintains its fundamental identity even as its phenomenal appearance transforms beyond recognition. Sleep changes the body's activity patterns, but does not alter its genetic code. Cosmic sleep changes the universe's phenomenal state, but preserves its mathematical foundations. This preservation amidst transformation offers perspective on our own ephemeral existence. As conscious beings, we too maintain identity through constant material change. Our bodies completely replace their constituent atoms over time. Our brains rewire their neural connections through experience. Our thoughts, feelings, and perceptions constantly flux through conscious awareness. Yet something we call self persists through these transformations, maintaining continuity despite constant change. Our personal identity, like the universe's cosmic identity, resides not in material permanence, but in patterns preserved through transformation. Perhaps all existence involves this dynamic between permanence and change, between preservation and transformation, between continuity and evolution. Nothing remains absolutely static. Nothing changes without maintaining some consistent aspects. The sleeping universe continues changing, albeit extremely slowly. The active universe preserves certain fundamentals despite constant flux. Identity itself emerges not from absolute stasis, but from continuity amidst transformation, from the preservation of essential patterns despite alteration of material instantiation. We exist, like the universe itself, as processes rather than static entities, as patterns in flux rather than unchanging substances. This process perspective illuminates how states apparently opposite, like cosmic activity and cosmic sleep, represent not absolute contraries, but points on a continuous spectrum. The universe does not switch discretely from wakefulness to slumber, but gradually transitions across intermediate states, progressively slowing its processes, dispersing its energy, simplifying its structures. Similarly, consciousness potentially adapts to changing conditions, rather than simply terminating when its familiar substrate dissolves. Transitions, rather than absolute boundaries, characterize cosmic evolution at its deepest level. Recognizing these continuities transforms how we understand endings generally. The universe never truly ends in absolute terms, never ceases existing, never terminates completely. It transforms, evolves, transitions through different states of activity, different material configurations, different phenomenal manifestations. Even in its final state, quantum indeterminism ensures some minimal activity continues indefinitely. Some possibilities remain unrealized, some potentials unexplored, some configurations unmanifested. The sleeping universe continues dreaming in the language of quantum fluctuations, its potentiality never fully exhausted, despite near equilibrium conditions. This perspective suggests something profound about time itself. Rather than flowing uniformly from beginning to end, time manifests differently across cosmic epochs, stretching and transforming as conditions change. The early universe processed time rapidly through extreme energy density and temperature. Our current epoch measures time through steady stellar burning and orbital regularity. The far future stretches time almost beyond recognition, with meaningful events separated by durations dwarfing our cosmic age. Time itself sleeps in the universe's final configuration, its flow slowed to near imperceptibility, its causal connections attenuated almost to breaking point. Yet even this transformed time maintains certain essential characteristics. Events still bear causal relationships to other events, though separated by vastly longer durations. Entropy still increases, though at vanishingly slow rates. Quantum systems still evolve according to their wave functions, though with minimal environmental interaction. Time changes its character, its pace, its phenomenal manifestation, but preserves its fundamental directionality, its causal structure, its role coordinating physical transformation. Like the universe itself, time persists through radical transformation, maintaining essential identity despite altered expression. This strange timeline, stretching from Big Bang to heat death, from maximal activity to near-perfect quiescence, defies human intuition. Our minds evolved to comprehend durations relevant to survival, timescales measured in seconds, days, years, occasionally centuries. Cosmic time operates across scales exceeding our intuitive grasp, requiring mathematical representation to comprehend meaningfully. Yet remarkably, our consciousness can extend beyond its evolutionary context through abstract understanding, can comprehend intellectually what it cannot directly experience. Through mathematics, through theoretical physics, through philosophical reflection, we conceptually access timescales our bodies can never directly witness. This capacity for transcending our immediate context through abstract understanding itself reveals something profound about consciousness. Despite emerging from evolutionary processes operating across merely biological timescales, consciousness can comprehend vastly longer durations through conceptual extension. Despite existing briefly within cosmic history, awareness can encompass that entire history through theoretical modeling. Despite occupying minimal physical space, mind can conceptualize the entire observable universe and beyond. Consciousness transcends its physical limitations through its capacity for abstract representation, for manipulating symbols that reference realities beyond direct experience. The sleeping universe thus reveals itself to conscious contemplation during cosmic youth, becomes comprehensible to awareness during the brief epoch when conditions support consciousness. This comprehension itself represents something remarkable, a system developing components capable of modeling the entire system, parts that understand the whole containing them. The universe achieves self-knowledge through the fleeting emergence of consciousness before returning to unconscious slumber, having briefly illuminated its own nature through the light of awareness that temporarily evolved within it. This brief illumination, this momentary self-comprehension, potentially carries meaning beyond its temporal extent. Information once generated persists in various forms, through subtle correlations, through quantum entanglement, through patterns preserved across transformation. The universe that sleeps remembers everything it experienced while awake, contains within its structure the complete record of its active history. Like human sleep consolidating memories from waking experience, cosmic sleep preserves information generated during more active phases, maintaining continuity despite transformed awareness. The anthropologist Gregory Bateson defined information as a difference that makes a difference. In the sleeping universe, most differences diminish toward imperceptibility. Thermal gradients dissipate as temperature approaches absolute zero. Material structures dissolve as particles decay or disperse. Energy distributions homogenize as cosmic expansion stretches space toward effective emptiness. Yet some differences persist even in this near equilibrium state. Quantum fluctuations continue creating momentary deviations from perfect uniformity. Field configurations maintain subtle variations across vast distances. Information, though dispersed and attenuated, never vanishes completely from the cosmic system. This persistence of information, of pattern, of structure, however minimal, ensures the sleeping universe never reaches absolute emptiness, absolute homogeneity, absolute equilibrium. It maintains some internal differentiation, some spatial and temporal texture, some configuration space not completely explored. In information-theoretic terms, the universe preserves entropy below its theoretical maximum, maintains some organization regardless of how dispersed, retains some potential for further evolution despite near equilibrium conditions. The cosmic sleep, like human slumber, contains internal structure beneath its apparent stillness. What meaning emerges from this perspective, from contemplating a universe that transitions from vibrant activity to quiet slumber while preserving its essential identity? Perhaps meaning itself transforms across cosmic epochs, manifesting differently within different contexts, expressing itself through changing modalities as conditions evolve. During our current stelliferous era, meaning often connects to complexity, organization, pattern recognition, relationship. Different meanings may emerge within the sleeping cosmos, operating through principles appropriate to those radically altered conditions, recognizable only to awareness adapted to that environment. Rather than imposing human conceptions of meaning onto the universe's final configuration, perhaps we should consider how meaning itself evolves alongside cosmic conditions. The sleeping universe contains its own phenomena, its own principles, its own relationships, unlike those dominating earlier epochs. These relationships necessarily differ from those supporting conventional meaning-making, but may harbor their own significance within their specific context. Like dream logic differing from waking rationality, yet maintaining its own internal coherence, the sleeping cosmos potentially contains forms of order, pattern, and relationship generating meaning, according to principles appropriate to that state. This perspective suggests meaning resides not in any particular cosmic epoch or material configuration, but in the relationships, patterns, and processes operating within each context. The early universe generated meaning through fundamental force differentiation, particle formation, and nucleosynthesis. Our current epoch creates meaning through stellar evolution, planetary formation, chemical complexity, and biological organization. The far future will harbor different meaning-generating processes operating through quantum fluctuations, information preservation in field configurations, and whatever consciousness forms might persist under those conditions. Meaning adapts alongside the physical universe, rather than disappearing when familiar structures dissolve. This adaptive quality connects meaning to information, to pattern, to relationship, to difference that makes difference rather than specific material configurations. Information persists through cosmic evolution, though transforming its encoding, its density, its accessibility. Patterns continue, though changing their manifestation, their complexity, their temporal development. Relationships endure, though altering their components, their dynamics, their causal structure. The universe that sleeps still contains these fundamental meaning generators, these basic constituents of significance, albeit operating differently than during more active epochs. Perhaps most profoundly, the sleeping universe embodies potentiality, the capacity for further evolution should conditions change, the preservation of possibility within apparent quiescence. Even in near-perfect equilibrium, quantum fluctuations occasionally produce complex configurations through extraordinarily improbable, but never impossible random assemblies. Given infinite time, even the most unlikely events eventually occur. The sleeping cosmos thus maintains potential for renewal, for unexpected complexity, for novel phenomena emerging from quantum possibility. Like a dormant seed containing life potential within apparent inactivity, the universe preserves development capacity within its resting state. This potentiality connects to various cyclical cosmological models, from oscillating Big Bang Big Crunch scenarios to Roger Penrose's conformal cyclic cosmology, from eternal inflation, creating new bubble universes, to string theory landscapes with transitions between different vacuum states. While current evidence favors eternal expansion toward increasing entropy, these alternative frameworks suggest the universe's sleep might eventually give way to renewed activity, might contain seeds of regeneration invisible from our limited perspective. The cosmic slumber might represent not a permanent condition, but a phase within larger cycles exceeding our observational capacity. Even without such literal renewal, the sleeping universe preserves the complete record of everything that occurred during more active phases. Information about every star, every planet, every living being, every conscious thought remains encoded within the universe's structure, preserved through subtle correlations between particles, through field configurations, through the precise distribution of radiation throughout space. Nothing truly vanishes from cosmic memory, though access to this information becomes increasingly difficult as it disperses across expanding space. The universe remembers everything it ever was, carries its complete history within its present configuration, regardless of how transformed that configuration becomes. This cosmic memory connects to philosophical traditions, emphasizing the eternal significance of temporal events. From Plato's forms existing outside time, to Nietzsche's eternal return, from Spinoza's perspective on eternity, to Whitehead's concept of objective immortality, various frameworks suggest momentary occurrences achieve significance, transcending their temporal limitation. Each present moment, once actualized, becomes a permanent fact within reality, an accomplished actuality that cannot be undone or erased, regardless of future developments. The sleeping universe preserves these actualities within its structure, maintaining their reality despite its transformed state. The physicist Paul Davies captures this perspective when he writes, "The past exists only as a record, albeit sometimes, as in human memory, a systematically edited and reordered record. The future exists only as potential, that is, as a range of genuine possibilities. Both the past and the future connect to the present by physical law." This insight applies with particular power to the sleeping universe, which contains both complete record of cosmic history and complete potential for whatever further evolution quantum indeterminism makes possible. Past and future meet in the cosmic present, regardless of that present's specific configuration or activity level. Our own brief existence acquires meaning within this vast context, not despite, but because of its temporal limitation. Like a musical note contributing to a symphony, our lives form part of the cosmic pattern precisely through their specific temporal location within the broader composition. The universe awakens to self-awareness during its youth, observes and comprehends itself through conscious minds, then carries this self-knowledge forward implicitly through information preserved in its structure, even after conditions no longer support explicit consciousness. We participate in this grand narrative through our momentary illumination of reality from within, our brief but significant contribution to cosmic self-comprehension. The strange behavior of physics at the end of the universe thus tells us as much about meaning as about matter, as much about significance as about entropy, as much about value as about energy. It reveals how meaning transcends particular physical configurations, persisting through transformation rather than requiring permanence. It demonstrates how significance resides in relationship, pattern, and information rather than specific material arrangements. It suggests how value emerges from the contribution each moment makes to the complete cosmic narrative rather than from temporal duration alone. The sleeping universe preserves these aspects of reality despite its radical transformation from earlier cosmic epochs. As we conclude our journey through deep time, from the physics of our current cosmos to the strange conditions of the far future, we discover not meaninglessness but altered meaning, not absence but transformation, not ending but transition. The universe that sleeps maintains continuity with its more active phases, preserves its essential identity despite phenomenal transformation, contains both complete memory of its history and full potential for whatever further evolution remains possible. Like human sleep, cosmic slumber represents not termination but alteration, not conclusion but continuation in modified form, not death but preservation through changed activity patterns. When all the stars go out and all the particles drift apart, the laws that once governed everything may sleep too, and in that final silence, the universe remembers everything it ever was.